Morning, everyone. I think we're going to make a start, so if you can take your seats. Welcome to the Dyson Institute of Engineering and Technology here in Malmesbury. And welcome to the UK Acoustofluidics Special Interest Group meeting, June 2024. So my name is Peter Wilson. I'm the Deputy Director of the Institute. I'm the head of the academic team here. We're in the Institute territory. You may have noticed as you came past that the main Dyson HQ, R&D, is next door. Our main sort of working in part of the Institute is actually over in the main Dyson building. This is really the student village, so the accommodation pods. I'm very jealous, by the way. They look really cool. And this is a combination of event space and students, so it's kind of the equivalent of the Students' Union. Not quite, but it's kind of equivalent to that. At least the upstairs definitely is. So that's where we are. And we're relatively young, well, very young as an institute. So to give you an idea of the timeline, it's really only since 2016 that the Institute started with a challenge. Basically, Sir James, he was in conversation with the then Universities Minister about the lack of engineers coming through the university system. And so he was challenged to start his own university. And within a year, we were off and running in partnership with WMG, University of Warwick Manufacturing Group, to develop a program of a degree apprenticeship in partnership with them. And that has led to us being awarded provisional degree awarding powers in 2020 to offer a program. And that culminated in the first graduates with the joint program coming through in 2021. And since then, in this last year, it's been a very exciting year. We've been awarded full degree awarding powers. We've recently swept the board with outstanding awards from Ofsted for our degree apprenticeship, which is really unique for a first time out. Accreditation from the IET and the BCS. And as a result, this coming autumn, we're offering a whole range of new programs, a new MEng in engineering, a postgraduate MSc in software engineering, and some other programs along the way, and also beginning to develop collaborations for research. The challenge for research degree awarding powers is it's a longer road. You have to do 30 collaborative PhDs to completion before you can apply to award PhDs. It's a pretty long, hard road, so we're beginning to develop collaborations with university partners. Some of you may be already involved in that. And so if you're interested in doing a collaborative PhD with us, come and talk to one of our academic colleagues today, and I'm sure we will be reaching out to some of you as well. So that's where we are. Very exciting time, very rapid rise. We are not able to be called a university yet because of the strict rules about using university title. Another 3 years and we'll be able to apply, so that's why we're the Institute. But we are effectively a Dyson University. How the program works here, it's unique. It's similar to degree apprenticeship, but all of our programs are fully integrated with the workplace. So the students that you'll meet today on the current program, they're doing 2 days of study in the Institute and 3 days of work, all co-located in here at Malmesbury or at Lavington or Bristol. And the way that the program works is that for the first 2 years, it's a general engineering degree, covering all aspects of engineering: mechanical, electrical, software, electromech, mathematics. And then in years 3 and 4, the students can choose a specialization. So that could be a mechanical engineering, electronics, hardware, software, or electromechanical. So this allows the students to specialize in a discipline of their choice. And this is aligned with rotations, what we call rotations in the workplace. So the first 2 years, there are 4 distinct rotations. So the students, again, are getting a flavor for those different disciplines all throughout the business. So it's a really immersive, engaging experience. And in the final year, the students are lucky enough, our 3rd years, they're just about to jet off to Singapore for, is it 8 weeks, Jake? Yep. 8 weeks. at the Dyson headquarters, and also to see how the manufacturing facilities work and some of the other sites in Southeast Asia. So I'm very jealous, but it's a really important step to engage with a global business. I think that's a really, really useful experience. And then they'll come back for their final year and do a final year project. And that project will be linked with something relating to the business, which is really exciting, many in the research aspects. If you want to find out a bit more about our research strategy, there is a QR code, and you can find it on our institute website, dysoninstitute.ac.uk. So I'll leave that up there so you can take a picture of the QR code. And really hope you enjoyed the meeting today. The program looks really exciting. If you've any questions about your navigation and getting around the roundhouse and where everything is, please reach out to one of our students. You see them, they're all wearing the very blue, you notice we like blue, T-shirts, so they're very easy to identify, or one of the staff members will be only too happy to help. So hope you really enjoyed the day. And with that, I'm going to hand over to Dr. Mehdi Baroun, who's the chair of the meeting. So over to you, Mehdi.
Thank you again, and thanks for coming. So before we start, I guess we're 10 minutes delayed, but there is no rush because one of the morning's talks is cancelled. So hopefully we should finish for lunch in time. A few housekeepings before we start. So I guess you all noticed that the toilets are back there. It's absolutely fine to take photos inside this building, but please don't take photos outside. The security rules here are quite strict. Sorry about that. I guess we will have some breaks for the coffee, but in between, if you need some coffee or any refreshments, please go to the canteen back there and you will get the coffees. And also, I have this, what happened to this pointer? So if you're presenting, this is just a trick one. There is a distance between the stage and the screen. First of all, be careful there. And then if you want to point something, use this Dyson vacuum cleaner handle. Okay, so our first talk is by Richard, so Professor Richard Fu from Northumbria University, and he is going to talk about Mission Impossible for acoustofluidics. Thank you.
Okay. Okay, thank you, Radin. So it's very nice to be here. So last year we had a very successful, SIG meeting, and this year we hope it's another much better and exciting one as well. So firstly, that I want to find a very good topic. So last year I gave a talk on the Olympics of acoustofluidics. So this year I'm thinking is what it would be something new. So my background is more on the advanced materials and also some film development. So I use a kind of technology, micro machining or MEMS, microelectromechanical mechanical system, to making the different microstructure, micro devices, sensor, actuator. I also using the different ways to make nanostructure, nanomaterials. So this is more like for sensing, for energy harvesting, for solar cell or different applications. So one of the special area which is related closely with our topic here is, so I was using the thin film, which is piezoelectric thin film, which is perfectly for generate the ultrasonic or acoustic waves. So I was thinking that, is there any good name? So I was thinking, oh, there is a movie, right? A lot of film movies, Mission Impossible. So I was thinking that what could we develop something which is difficult to realize using the other technology? Okay, so background. We need some background to tell why we need this. So basically, we always using an example which is called lab on chip. So if you have disease, right? If you go to hospital, then the doctor or nurse will take a lot of blood from your body, so a few bottles, right? So what they do is that they put into different tubes for analyzing. Well, so the idea for lab on chip is that we actually don't need so much blood volume, right? So basically, we can dilute it and then separate, transport, and then mixed, and then reaction, and then after reaction, then remove it, and then doing sensing, right? So everything will be done in a small chip. And then because it's small chip and also volume controlled, very precision, so we claim that maybe a few drops of blood, you can detect all the different diseases, right? So the only problem with it is that lab on chip is small, but the different function, for example, droplet mixing, moving, reaction, all these functions, you need to have different technology, right? So if you think a chip is small, but the operation equipment, there are huge number of different equipment. So this could be very difficult to achieve. So the question always like, is there any one technology which can realize all the different functions? So because we are doing acoustofluidics, right? So we claim that we can using a way which is surface acoustic wave device, which we can realize all the different functions. So, so basically that this is already very well developed area is that if we can generate a nanoscale earthquake effect on the surface, then there will be mechanical wave generated from the radio frequency signal, and then this wave propagation on the surface, then it will drive the liquid and then moving around for pumping, for mixing, for jetting, for nebulization, for all different things. And also advantage is that it also has very good function, which is biosensing. So that means every different function can all be linked and also using this technology, right? So another advantage is that it's not only acoustic wave itself. So as we can see that surface acoustic wave basically is a remote control, remote operation, because the electrode will be slightly far away from the operation area, right? So that means we can, like football stadium, right? So the acoustic wave can be audience. Then the central field, which is everything which can integrate it together. For example, you can put photonics, you can put direct you can put the SIG, surface enhanced Raman, or any structures, nano metamaterials, everything inside which football stadium, right? The surface acoustic wave just audience to give the energy, shouting, helping, and then encouraging, or do all these different functions, right? Okay, so so if we go back to the what is the surface acoustic wave, so basic idea is that we can using the piezoelectric materials. Either you can use in bulk, like lithium niobate quartz or PZT bulk materials, right? And then, or you can use thin film on any substrate, piezoelectric thin film on substrate. And then on top of this electrode, we need to have the kind of interdigitated transducer. So this transducer can generate, can have changing the electric signal into the mechanical wave, so through the piezoelectric effect. So the most significant influence is actually the mechanical wave propagating on the surface interaction with the liquid, because the liquid will absorb the energy, and from physics point of view, then there will be a pressure or force generated at one angle, which we normally call the Rayleigh angle, which is corresponding to arc sine of wave velocity in the liquid divided by this velocity in the solid. So if it's silicon substrate, if it's water, this angle is 21 degrees, roughly. So for acoustofluidics, as we all well know, is that there are two types of study. One is called digital acoustofluidics. It sounds like quite simple, quite interesting, digital. But basically, just play droplet, right? So everybody can play droplet easily. And then the droplet moving, you can see clearly. Phenomena is so exciting because deformation, changing is dramatic. So what we, digital fluidics, acoustofluidics, is that we're using the droplet as a unit. We fix any concentration or information in this unit. We're moving this droplet around, mixing, enhancing reaction, and then this is digitally can be monitored. And then so basically it's just using the droplet as a function, which is quite easy. So because we're always using this one for illustration, what is surface acoustic wave, acoustofluidics, because you can pumping, you can moving the, let's say the blood sample mixed with water, diluted, and then you can also using the different functions, right? So this is one type of digital acoustofluidics. Another, it's actually very widely studied acoustofluidics is called continuous flow acoustofluidics. So basically is that what we do is that we're using microchannel or microchamber. So we put a liquid with certain volume, either flowing or static. And within it, we're either using a standing wave to manipulate the particle or cells, biological cells inside. We're patterning, with separation, we do analysis, we do the operation, we do kind of applying the different acoustic forces to trigger or do the drug analysis or delivery, all different functions. So this is most basically using the traveling wave or standing wave. So if it's standing wave, it's from both sides, the wave have different frequency, different wavelengths. And then they're causing the nodes and antinodes. So you can manipulate them in different places. And also you can using the traveling wave because all the particles have different streaming force and radiation force. So you're basically using the design of microstructure, a microchannel structure, or a designing of flow pattern. You can actually accumulate some of the very small particles into different positions. So it's actually continuous flow acoustofluidics is widely studied. And then we actually recently published with Cardiff University of review paper. We identify the streaming patterns which we can create. And then from different streaming patterns, we propose that so acoustofluidics can be used for different applications. For example, we can use it for kind of drug development. For example, if you can nebulize the liquid, right? Then the nebulized liquid has the drug molecule inside. So basically, it's like an inhaler application, right? It's very high frequency, and then you can get very drug delivery to your lung, which is much effective. Or you can using for separation. So people using this for separate bacterial cells, cancer cells, or stem cells, or cells with bacteria or bacteria with virus, or even further smaller and smaller. So they can use it for different separation. And then someone proposed using the acoustofluidics to the, we call the chemical reaction. So as we know that if you want to make a 2D materials, right, it's quite hard. You're using different chemical vapor deposition PVD method. But a lot of people using acoustofluidics, just using surface agitation forces, radiation forces, then separate graphite into the single or multi-layer of graphene, right? So you can use it for 2D material synthesis or other. So, and also you can use it for printing. Either you're using injection, or you're using the different ways. Yeah, so, and also you can using the femtotapping. So that means you can using acoustic wave radiation force to deform the cell and then study the cell behavior or electrical or mechanical behavior. So this is very interesting. So, and then what is my topic? I was thinking that, okay, mission impossible. So what kind of mission impossible can do, right? So I download a lot of movies or GIF file here. So this, the first I want to show that we can using acoustic wave to make the invisible or transparent surface acoustic wave. So this is a very good application because as we know that there are a lot of equipment like glass window, high specific length, right? They are transparent, right? So you cannot see that, okay, I make a SAW device which is covered with different electrodes, then this won't work, right? Because those optical persons, they don't allow you to do it. So what we are aiming to do is that we can make all the acoustofluidics as a transparent, invisible. So how to do it is actually not so difficult because we're using thin film technology. So a lot of thin film like a piezoelectric, like a zinc oxide, aluminum nitride, PZT, or lithium niobate, whatever the oxide or nitride film, once the thickness is thin enough, and also quality is good, they are optical transparent. So this is good. So you deposit on glass, it's still transparent, right? And then electrode, because we need the electrode to generate acoustic wave, right? The electrode you can using, transparent, kind of oxide electrode. For example, you can use an AZO, ITO, right? They are all transparent. So basically, you can make the all transparent SAW device on top of the glass. Then once you make it, what is the application? Because the lens, optical lens, if it's used in the space or low temperature, you also is facing some fogging or dusting or icing or all these ones. Once you get this phenomena, then the optical property are totally lost, right? You can't use it. So there need a way which is how to immediately or very efficiently to remove fogging, cleaning the lens, and also de-icing the lens. So that means you wouldn't need to worry about, military or space technology. You couldn't operate optical equipment, right? So we can design, and then we deposit the oxide, zinc oxide or aluminum nitride on top of glass, transparent, and then we pattern the electrode. So the electrode doesn't need to be on the structure of lenses, right? So you can actually pattern, because as we mentioned, surface acoustic wave is remote way, right? You don't need to actually cover the optical essential area. You can put the electrodes further away from the optical function area. So that means you remote give all these functions. Then we're using this one to demonstrate that we can do de-icing. So basically, we switch on the SAW acoustic wave frequency, and then the ice form then quickly begun. We can do defogging. So this is quite a fast and efficient way. Of course, not only here is that we also work with, for example, Professor Zhou from Hunan University in China. And then we got a lot of flexible glass, which we are aiming to for the flexible wearable device application. You know, the glass, if it's very thin, you can actually bend easily, right? And then you deposit the thin film transparent and pattern with transparent electrode. Then everything is transparent, but we have the very wearable, flexible glass SAW device, right? So this is another area which we are working on. So basically, we published quite a lot of papers with Professor Zhou. It's on the how to bending the device and then making the sensing performance or influence of other parameter effectively. So if you want to know more, then you can search our paper. Okay, so next, Mission Impossible is jetting. As we know that if we apply the high power, the droplet won't just moving around, right? It doesn't have any chance for moving, it will be ejected through the Rayleigh angle, right? So that means the simple way is that we just apply the high power, not very high, but a few watts. And then the droplet will be ejected according to the Rayleigh angle, right? So Mission Impossible, they have something which is, okay, so, and then, but people always think that, okay, icing, no, jetting, people you prefer the vertical jetting, right? So how to do vertical jetting? Basically, we're just using the wave from both sides. And then we can do vertical jetting, or we can use circular electrode design, and we can eject the surface from the, vertically, and then get the printing effect. We can also using different electrode, and then ejection the liquid from different angle, different pattern, different function. So because it's, so next is that Mission Impossible. How can we using the high power to generate something which is totally exciting, right? So, so the first, of course, is nebulization. So nebulization looks like a liquid has been vibrated, and then there will be a complete wave generated. Then there will be small droplet ejected. And then the higher frequency, you have much higher, smaller droplet. So that means you can create a lot of droplet, which is small size. Somehow it's not working. Okay, so another phenomenon is that we can heating the substrate, which we can easily get the temperature increased significantly. And then the highest temperature we can obtain is like 250 degrees, which is very high. And then using this technology, we can also doing icing. So yeah, so I mean, so the icing technology will be the very exciting one because so basically what we are trying recently doing is that we can make the acoustic device using the electrode is much larger, and then we can generate the wave and then on the very large scale surfaces, and then we can using this for anti-icing or de-icing purpose. So the basic idea is that we can design the kind of matrix of this electrode. So that means on the whole turbine, we can making a lot of devices. And each devices will be agitated and then to form the different, cover different area for icing. And then for doing the icing, we need to using the kind of integrated or combined hybrid method. So that means we're not only using the active method like thermal, electric thermal, or ultrasonic. We're also using the isophobic or hydrophobic treatment to make the surface is more hydrophobic. So basically the idea is that it's because it's nanoscale mechanical wave, its vibration and also the force will separate the ice from substrate. And also, as we mentioned, we have very significant heating effect, localized heating. So that means we melted the interface layer. So once in the flight condition, so the ice, once it's separated from interface, it will be easily removed away, right? And then we can easily demonstrate, for example, this frozen droplet. If you without acoustic wave, and then it will take a very short time to frozen. If we're using acoustic wave with very low power, sub-watts, and then you can easily get the different phenomena. We're also doing the de-icing, so that means we let ice form on the device surface, and then we apply the acoustic wave, then we can easily generate the wave. So I just showed the movie, I hope it's working. So you can see the wave propagation and then this forest of the icicle. And then once there is any kind of wave propagation, then all the forest is falling down, and then there will be also the melting effect. So this is very significant or exciting phenomenon. So the idea behind it is that we can generate a acoustic wave propagating onto the components like a wind turbine or airplane wing. And then we have the matrix of this electrode, and we cover different areas. And then the power we use is very low. We can use the wireless to give the resources to melting the local area and also separate the ice from substrate.
Richard, 1 minute.
Okay, yeah. So it's already very long time. So basically, is that once we go into further and further, we realize that, okay, so the wave is not at the beginning we saw the surface wave. So there are a lot of different wave modes. There are bulk wave, there are lamb wave, there are a lot of different wave modes. So that's why we actually working on a different way to study the different wave modes interaction with liquid and droplet and or liquid and in the chamber. And then so I should thank all the collaborators worldwide, and then there are a lot of funding support for us. Yeah, thank you very much. Yeah.
Thank you. I think we can just have one quick question. And also from the online audiences, if you have any questions, please type your question in the chat. Yes, Jake?
Someone else have a question now. I was just going to say, when it comes to, also thank you for the talk, by the way. When it comes to the de-icing stuff, in terms of power consumption and efficiency, oh yeah, thank you. In terms of power consumption and efficiency, and when it comes to de-icing, with this sort of surface acoustic wave implementation, after you've taken account for losses in the generation of the radio frequency, do we still see an increase in efficiency versus, say, just like the sort of brute force approach of just having heating elements on the surface and just pumping heat in until the ice melts?
Yes, so we actually studied the principle for this de-icing principle. So there are two influences. One is interfacial heating effect, thermal effect. One is acoustic vibration effect. So once you apply acoustic wave, then those two effects are combined, so you cannot separate them easily. Well, we have studied separately. We also studied the electrothermal. Compare with this one, that power is much higher needed. And then we also studied what is the temperature effect, because we're using the substrate cooling to make the substrate ice still maintain very low temperature, right? So basically, is that it's still effectively just because it's a micro interface scale, the heating effect. So I mean that how to separate them and how to study them. So we also need to study that because our device is very small. Once it goes to a large scale, how much power is actually consumed? So this is another question for application. Yeah.
Oh, thank you for that. That's really interesting.
Thank you very much. Thank you, Richard, again.
Yeah, thank you. Yeah.
So I think Julian is delayed. Has he checked in? Okay, I know that Julian is around, but probably he's delayed. So let's move to the next. Okay. Yeah, that's okay. Yeah. So next have Xiaoyan Zhang from Cardiff University, and he's going to talk about acoustofluidics devices for perturbation from cell level to tissue level. Thank you.
Okay.
That's the point.
This is? Okay. Oh, yeah. Hello, everyone. My name is Xiaoyan Zhang, and I'm very pleased to be here. I come from Cardiff University, and today I will introduce the two projects I did during my PhD period. The title is Acoustofluidic Devices for Perturbation from Cell Level to Tissue Level. The first, I will introduce the cell level perturbation, and the target here is a suspension cell. And because cells, they are suspended, so the perturbation caused by acoustofluidic may cause very big effects to the individual cell. So based on this, we found the one application for the fast pre-cytopathological screening. And then here, we collaborated with two hospitals in China. The motivation of this project comes from, in currently clinical setting, in hospital, the true negative rates of the true diagnosis results is pretty high, usually more than 70%. That means a lot of medical resources just wasted for the true negative results. So it's imperative to find one pre-cytopathological screening method. So based on this, we want to use acoustofluidic for perturbation to rotate cells to provide multi-view morphological information if it can aid the cytopathological screening. So based on that, we make the MARC system, and MARC system is based on the 2 PCB IDT, and it could generate the saw to form 2 cell traces pattern, just follow along the 2 pressure nodes, and streaming makes the cell just in situ rotation. So how to make it happen, make this phenomenon, just 2 cell traces while in situ rotation. So we use the COMSOL simulation to predict the specific actuation dimension. And here I listed the, just like for the microchannel dimension, you can see here the oven, blue oven, it represents the pressure nodes. But in some combination, the first 2 of the red parts, yeah, it has 4 pressure nodes. That means it's pretty hard, may overlap each other. So for the last one here, it has 2 pressure nodes. But you can see as the red arrow represents its streaming vortex, that around per pressure nodes, the streaming vortex may counteract each other, so it can't work. Based on exploration, we found in this specific dimension, the width 200 micron and the height 60 micron, it could form the two pressure nodes. Just after acoustic on, it could pattern two cell traces. And we did the zoom in simulation for the half part of the macro channel. And you can see, okay, yeah, just around the pressure nodes, it has a big stream vortex, yeah, as the red arrow represents, and it can drag the cell, just rotates in the reverse direction. So the final effect will cause the two-cell pattern has throughput cell in pseudo rotation at this specific macro channel dimension. So we already achieved this in pseudo cell rotation phenomenon. So what we can do next? Firstly, we tested it just without any staining. We try to see if it can provide some useful, just like morphological information. We found, yeah, it's true. Just like here, you can say without staining, we can even during the rotation process to see some cellular information as the nucleus numbers. It will vary, maybe 2 or 1. And as this video shows, at some rotation angle from the observation, you can even see the cell nucleus outline. So that's without any staining. So based on this, we want to know if without staining, based on our mark capability, if it can discriminate cancer cell and healthy cell. And we tried to use the cell circularity, this parameter, and we combine the one rotation cycle into 8 parts, and we quantify them together. As here it shows, you can see, yeah, based on the multi-angle quantification, those two cells, their circularity parameter vary significantly. Then we tested if our device could achieve a controllable rotation control. So yes, we did. We found by adjusting the input voltage, we could control the rotation speed of the two cell traces. And also for this rotation position deviation for each individual cell, it could also be controlled by adjusting the input voltage. And we found the 15 VPP, this input voltage is best because the two cell traces, they show no difference. That means the two cell traces, they are very controlled, very good controlled. So it means the cell rotation speeds and stability could be accurately controlled by adjusting the input voltage. So as the previous slide shows, without staining, we could see some useful morphology information. But for cytopathology screening, you need to stain the nucleus. So we stained the cell nucleus for next and use the 3 commonly used parameters, the solidity, circularity, and answer ratio. Those parameters are all the pretty notable indication to indicate if cell, they are more likely to be healthy or tumor cell. And we use here the PCA, the first projection, the PC1 to combine those 3 parameters together to evaluate if the rotation angle causes a very big difference. And the result shows, yes, those 3 parameters all show significant variation under multi-view evaluation. So we did further quantification for each parameters separately. And we found, you can see here, the answer ratio, it has the largest width area. That means this parameter, varies significantly by the rotation angle. So it means the answer ratio is influenced among those 3 parameters most by the observation angle. So based on this conclusion, we further use the answer ratio to do the test and do the comparison with the traditional cytopathology detection to test its capability for distinguish different cells. And you can see here, the result shows that with using the rotation-based answer ratio, our mark system can significantly improving the discrimination capability to discriminate cancer cell, cancer and healthy cell, and also can amplify the variation among the different cancer cells significantly. So Okay. So do the summary for the MARC system. The MARC, I think, is a promising just pre-cytopathology screening method. And you can see here, because we could pattern cell into two traces and provide the multi-view morphological information, so it could improve the sensitivity for cytopathological screening. So we proposed here a vision, just the cell sample first experience our MARC detection because MARC is more accurate, yeah, based on the multi-angle observation. So only MARC detected the positive results need to further experience a traditional cytopathology detection. In this way, more medical resources will be saved, to avoid to filter those true negative results. The second project, is about the tissue level perturbation. And here we choose the targets is a mass tissue level. And because the tissue, we all know, they are composed of multi-layers of single cells. So the perturbation by acoustofluidics may pretty hard to cause direct effects onto the tissue level. So we try to find the application point here, and we found one application point, is non-invasive transdermal delivery. And I also collaborated with one hospital in Shanghai, in China. And this project, the motivation comes from just currently the mainstream, the transdermal delivery method is microneedle, but the microneedle, you can see here, is always invasive, and after treatments cause very long time recovery periods and side effects. So it's imperative to find one transdermal delivery method that needs to be non-invasive and fast delivery. So based on these needs, we make the MARC system and the ABDG system. And the ABDG, this transdermal delivery system, is characteristic. It's not contacting. It don't need to contact to your skin, but it can form the bubbling droplets and to form the intensive cavitation onto the stratum corner layer for the transdermal drug delivery. So we do the quantification firstly to evaluate if we could control the bubbling droplets, its behavior. And you can see here, as the first video shows, just like in the liquids, it can form pretty intensive cavitation. And that means the second video means when the bubbling droplets, it enters the liquids, it could forming the air entrapment for the later cavitation. So it means we could, by adjusting the input voltage to control the droplet behavior. Based on this, we first try the transdermal delivery. The first drug is relatively small molecular weight. It's fluorescent sodium. And we evaluate from the horizontal for the skin level tissue, horizontal view, and from the cross-section view. And you can see here, from the horizontal view, the fluorescence shows, it shows pretty good agreement with the last slides. Just like by increasing the input voltage, the fluorescence intensity increased. And from the cross-section view, you can see compared with the control, our device family treatments could make the fluorescence evenly distributed to pretty long distance. So we do the further quantification. We found by using our ABDG device, family treatments could penetrate to already the dermis layer pretty long distance. And it compared with passive diffusion, the transdermal delivery efficiency improves 81.7 times. We also just tried by adjusting the actuation frequency can also cause very interesting effects. You can see here, the first US ultrasounds is one frequency. The model 1 is another frequency. You can see the first one, it causes evenly distributed to very long distance, but the second one, module 2, only to the short distance. So we do the further quantification. We found by adjusting also the actuation frequency, this module could control the delivery penetration depth. So we then tried a large cargo, the 10 kilodalton and 7 kilodalton FITC dectron. And it shows, compared with the passive diffusion, the control, it still be very effective, but it's not, it can't form very, just like the smaller molecular weights I showed last slides. Yeah, they can form evenly distributed, but here it can't. But still, do the fluorescent quantification, it shows, yeah, the delivery efficiency could be significantly improved by just 5 minutes treatments. Finally, we use nude mice to do the in vivo transdermal delivery. And here, because the actual vivo results, so here we chose just a relatively small molecular weights, the glucose. And you can see 5 minute treatments, we, through cutting the tail tip, use a glucose meter reading to evaluate the glucose level. You can see here, as the C shows, because for evaluation, the glucose level variation, all the mice need to treatment by the starvation. That means they can't eat any foods. So you can see family treatment for the control group, yeah, the glucose level drops. Well, for the ultrasound group, it increased. And we further did the quantification, found family treatments could increase 0.3 milligram glucose. And we further did the HE staining cross-section, and it shows our device is non-invasive. So do the summary for the ABDG, I think it's portable, and you don't need to contact just like here to contact your skin. And also, it will not cause any damage to your skin. And also, because by adjusting the frequency or input voltage, it could achieve the controllable penetration depth and efficiency. Okay, that's all. Finally, I will thank my supervisor, the collaborator, and the group members who evolved and devoted to those 2 projects. And thank you all.
Thank you very much. Any questions? Yes.
Really nice work. With the streaming work, is that boundary-driven streaming or streaming from the absorption of a higher frequency?
Yeah, it's from the high frequency. Yeah.
What frequency are you using?
Around 20 megahertz.
Thank you.
Any other? Yes, Richard.
So for drug delivery, right?
Yeah.
You see that it can be separated, remote control. But still is that the drug molecule, you need to have a layer, right, on the skin. So
Yeah.
You apply this drug on skin first, then you remote using ultrasonic.
So you mean how to just to avoid if the drug is attached to the skin, yeah, but not to penetrate.
Yeah, so you still need to apply a layer of drugs on top of skin.
Yeah, yeah.
So how can you monitor what is the damaging effect or heating effect or?
We already here I didn't show just but we already did the quantification for the just like the thermal effect. We quantified it's not the thermal effect because after 5 minutes treatments the skin layer temperature it did not increase. Definitely within 1 Celsius.
Okay, thank you.
Any other questions? Okay, so thank you again for your talk. Before I move to the next talk, just 2 housekeepings again. I can see that there is a car parked there. Probably that belongs to one of us. So if you recognize that car, can you move that car to the parking somewhere here? If you know that car. If not, forget about it. Second, Julian is here, but we're going to move Julian's talk to the last talk of the morning session. Next, we have Luke Howers from Northumbria University, and he's going to talk on harnessing active and passive strategies, nano-innovation for anti-icing and de-icing, hydrophobic nanoscale surfaces, and surface acoustic waves. That's a long title.
Yeah. Can you hear me, everyone? Yeah, I made the title slightly shorter from what was proposed because it was too long. So I'm from Northumbria. I'm one of Richard's PhD students, and this is 2 different schemes of work. Some of it was done just by us at Northumbria. Some was done in collaboration with Nottingham University, although they've now moved from Nottingham of Daya and Shanhui to China. So motivations, I'm going to talk about, and then the isophobic coatings, the passive method, and then SAW technology, and then what results we got from it. I'm sure you will recognize images such as this, so motivations, self-cleaning, cars get dirty, icing, icing's a big problem with aircraft and with wind turbines, and also inkjet printing as well. So surface acoustic waves have been shown to use for inkjet printing. Some current techniques, passive, so we've got superhydrophobic, hydrophobic, hydrophilic, liquid infused, for either preventing ice from nucleation from happening, preventing droplets adhering to a surface, and those are passive techniques. Active techniques, ultrasonic transducers used quite commonly in aviation for anti-icing and de-icing, and also some electrothermal methods. And this is an example of quite recent, I think it came out last year, of a composite electrothermal method, which is used for anti-icing and de-icing. So those are some of the methods that are used. But what do I do, and what do we do, and what do we do differently? So the first thing is, one proposal, and this came from the paper, is if we coat a surface with a given hydrophobic coating, how does that reduce ice adhesion? And reducing ice adhesion is important. And by how much does it reduce ice adhesion? What are the values? And that is a passive system, and then we have an active system. And the active system, you'll recognize this from Richard's presentation, is surface acoustic waves. So before I started, Richard published this paper with a postdoc and the guys from Nottingham, where they showed that you could use surface acoustic waves for de-icing of droplets, and we use the same technology, and I use the same technology, but for rime ice instead. So it's always important to look at surface coatings, and what coatings am I talking about? I'm talking about three. Glaco is a superhydrophobic porous coating with contact angles of 160 degrees, shown by the SEM image. And then I'll use this nice handy hoover. And then we have Cytop, which is a fluoropolymer coating. And then we have SoCal, which is a PDMS coating. The Cytop is randomly oriented fixed chains, and the SoCal is a more rigid vertical chain system. And that's for the passive. And then for the active, well, how do we make these surface acoustic wave devices? We start off by thin film deposition, as you can see here, where essentially we heat a zinc target, and then that deposits with air, as well as with oxygen and argon, that deposits zinc oxide on the surface. But that's not the whole thing. You need some IDTs, so we do a conventional photolithography lift-off method, where we then get patterned IDT structures, as you can see in this picture. Let's talk about the passive first. So one thing is, a lot of people use surface coatings and they say, oh, these coatings are very good, they're excellent, they can reduce adhesion, yada, yada, yada. But how durable are they? And that's always a question you get asked. So in order to test the durability, very simple. Measure the contact angles on the surface of a droplet before, and then freeze ice and snap it off. Freeze ice, snap it off, freeze ice, snap it off, and keep repeating this process and measure the contact angles afterwards. The contact angles illustrate the wettability, and so if there was degradation or damage to the coating, we would expect this wettability would change. But actually what we see here is that before and after, the contact angles remain pretty much the same. So you have the black versus the red for before and after for the advancing, the solid dots, and then the hollow ones for the receding. And you can see that they are within error bars. There's no great change, which is good. It means it's durable. And that's across all the coatings. And as part of this study, it's not good enough just to do smooth. Anyone could put something on smooth surface. So I roughened the surfaces. I used some sandpaper to introduce some macro scale roughness, and then saw how the coatings performed on that. Because the hydrophobic coatings are sub 5 nanometer. So if you then have micro scale features induced by sandpaper, the length scales are much bigger than that of the coating. So actually, does that lead to more inherent weakness of the coating or not? And we can see that although the error bars are bigger, there is no change relative to before the testing. And then you also have the hysteresis. That's the difference between the advancing and the receding contact angles. And you can see here once again, although the error bars are quite big, the results are similar. So what did I find? This is the first graph. So on here, I plotted the theoretical work of the ice. And the theoretical work of the ice is a relationship between parameter A, the surface tension and the receding contact angle. And then I compared that with the smooth results. And you can see that for the untreated and for the Glaco and for the Cytop, they all lie roughly where you would expect. Here is just highlighting the area where the ice has been snapped off. But this was an anomaly. So SoCal was much, much lower. The theoretical line's here, but the value is here. So we thought that's strange. Why? And essentially, SoCal is nanoscale PDMS brushes. And people have shown in literature that these brushes can be flexible. So if you push an ice block off one of these brushes, actually the brushes start to deform, start to bend, and that leads to very low ice adhesion result. Less than 1 kilopascal, which is ultra low ice adhesion according to literature. But as I said, anyone can do it on smooth, so why don't we do it on rough and see what happens with rough? And we can see that we have our smooth and rough untreated surface. We then treat it and we get a reduction in the adhesion properties. And then we can see differences. So we can see as the ice snapped off of the untreated, it leaves this residue or film, but you can see nothing there where the SoCal was. And here is our smooth SoCal, a lot lower than what we expected. So that was good. That was a good result, and that's the passive work. Then active work. Now, active was, as I mentioned, rime ice de-icing with acoustic waves. Rime ice is a porous ice. So it's generally the condensation and then subsequent freezing of small droplets of water build up a porous crystal structure. And we wanted to know, how does the SAW help deal with this? So here we can see that at varying humidities, we get different thickness of rime ice formation. And then we said, right, so what happens if we apply the acoustic wave? Now, we applied 0.002 watts, or 2 milliwatts, I guess, very low. And we found that at 60% humidity, it did well. This was anti-icing, so we were applying the wave before the ice build up. And you can see there's a very distinct difference. Instead of this ice, we've got pretty much nothing. But it didn't really work when you started to get higher humidities. So we said, right, let's take the extreme case, 90% humidity, the maximum density, and we'll apply different powers and see at what power do we not get this ice form. And we found that actually we can stop the ice forming at 0.66 watts, 90% humidity. So still pretty low power, and at 2.3 watts, it also doesn't form. 2.3 watts comes in later on for the de-icing. And so we thought, well, how does this happen? And we hypothesized that essentially what happens is the heating effect with the acoustic wave effect means that any ice crystals that do form collapse, and then the mixing with water, and then they will slowly melt, and then the water will evaporate. So we said, well, can we actually see this? Can we visualize this? This is what we think is happening, but how do we know? So here's some de-icing videos. The first one I'll play is just from a normal camera, 60 FPS and 2.3 watts. And you can't see much. I mean, you can see that it melts and disappears, but we thought, well, how do we look at the real details, the intricacies? Well, we have high-speed camera, so why not use a high-speed camera? So we go 5,000 frames a second, and the video is hopefully playing. You can start to see some falling of these structures, these crystal trees, I guess you can think of them as. You can start to see them falling and collapsing. So that's good. Our hypothesis for the anti-icing, that these crystals fall and collapse, we can see it happening there. And then you can see them starting to melt. So it starts to slowly melt once it's fallen over. And to see this in a bit more detail, we've got this video here. So this is slower because it's a lower power, but it helps really illustrate what's going on. So you can see here that there is a layer, it's different from the ice. So there's some liquid underneath the actual ice that forms, and you can see that the crystals collapse and then start to melt. And then it becomes water, and then the water just streams and then is evaporated. So we have a first stage where we have these collapse or falling of the clusters. And then we have an ice-rich de-icing front, but there is some liquid. So the crystals are still there on the surface, but there is some layer of liquid. And then afterwards, we get a liquid-rich front. So most of the crystals are starting to stream, are starting to mix in with the water and starting to evaporate. And then essentially we have this schematic where we have a thermal and vibrational effect. And that's how we de-ice the rime ice crystals. So some conclusions. The passive method, SoCal, significantly reduces ice adhesion on smooth surfaces, also reduces ice adhesion on roughened surfaces. And SAW can both anti-ice and de-ice at relatively low powers. So it can de-ice as low as 0.82 watts. It's not as quick as 2.3, but it can do it at 0.82. And it can anti-ice at 0.66, and it's a 3-phase regime. With that, I'll come to some acknowledgements for the collaborators, the funding, the DOI of the papers, a QR code that takes you through to my Linktree, which has the Google Scholar on there, and also LinkedIn if people want to add me on LinkedIn to talk about it, and a bit about what's next. Next is to integrate both of them. So we look at integrating this hydrophobic layer with the acoustic wave for anti-icing and de-icing and have a truly hybrid system rather than doing them independently. And that's the end of my talk.
Thank you very much. I guess we have time for a few questions. Yes.
Surely it's the power flux. It's the power flux that matters, isn't it? Can you tell me what those fluxes are?
No, we didn't look at the power flux per square meter, I'm afraid, no. I mean, the size of the sample was 2.5 by 5 centimeters that was doing 0.82 watts, so could work it out, but yeah, didn't actually measure it in that study per square meter.
Thank you.
Any other questions? I've got one. So for that video which showed about like the 500 FPS for the de-icing,
yeah.
How did you make sure that the radiation is not making like a difference? Because you should have like a quite intense light behind the ice.
Yeah. So essentially, I don't know if it's actually playing now. I think it is. Essentially, we did it many times. So we looked at making sure we adjusted the light and everything, and we put the camera actually in parallel with the surface so that there was no glass or anything in between.
Okay. Thank you. Any other questions? There is one more.
I guess partly the mechanism here is the acoustic wave becoming heat, which
Yes.
melts the ice. Are there reasons why you'd expect this technique to be more effective than just heating the surface?
Yeah, so the thing with just a heating effect is that ultimately it's a slow melt, right? The crystals are going to just collapse vertically down as it melts. So what we expect with this is that it's more efficient because we're forcing those crystals flat rather than vertical, and then they start streaming within the liquid. And because the liquid that's there is a relatively higher temperature than the ice, then it actually aids in the further melting of the crystals rather than just a heat effect.
Great, thank you.
So thank you much for it again. Next we have, are you going next, Julian? Yeah, of course, go for it. So next we have, no, that's okay. Let's have Professor Julian Rebound from Glasgow. The topic is Acoustofluidics Nano LSPR scanning microscope.
Sorry for the mix-up today, and thank you for your patience in getting me there in front of you. I know we're on time almost, so I'm not going to delay that too long. And today I talk about acoustofluidics and nanoparticles and how we can use that to do a bit of imaging. And so the idea behind this, or the motivation for that, is the fact that we are very good at doing analysis of biological media using surfaces, for example, that can be enhanced with light properties, or we have very powerful microscopes. And these two things are basically our tools to do imaging of cells, of molecules on surfaces, etc. Recently, there's been a few interesting ideas where the actual optical component can be moved around a surface and potentially do that in 3D. And so there's been some work that I'll go into a little bit more detail for the next few slides. But these are rather conventional optics, so a standard microscopy. And so what I'm trying to do here, or what we're trying to do in the group, is to use plasmonic effects as a sort of microscopy. And so far, plasmonics has always been as a surface. People will have heard about local surface plasmon resonance or SPR in a machine, for example. And so here, we're trying to do that in a slightly different way. So this is primarily work done by PhD student Chandresh in the University of Glasgow under co-supervision with Professor John Cooper. So the first thing that I want to acknowledge, I'm sure Richard has talked about this a little bit. I'm sorry I missed this. But surface acoustic waves in particular can be used to manipulate objects. And this very famously is often ending in a picture. And the picture very often in scientific literature says Duke. And the reason it says Duke is because the pioneer of these technologies is Tony Huang. And he's been extremely successful at doing this. And he's got all the know-how available in that area. It started very simply with, similarly to the work that Bruce in Bristol does, manipulating big particles, because sound is easier at lower frequency, and so large wavelengths, and so large particles. And in biology, or in the acoustics field, and acoustofluidics field, there was always this hope, or this challenge of going smaller. And lots of people were working very hard to get to nanometers. And so there was a lot of papers that were saying nanometers when actually what they meant is 900 nanometers, which was quite close to a micron, and trying hard to do that. There is another angle to that, which is resolution. And actually, resolution is extremely good. So if you have a particle of 5 micron and another one of 5.1, you're actually able to differentiate them using acoustics pretty easily. But going down below a micron for manipulating particles was very hard until Tony cracked it. And so this is quite a complicated system. I mean, the system in surface acoustic waves is very simple, and that's the graph that we have here. We have the usual 4 IDTs that enable us to control the particles in 2D, a little bit of 3D in trying to control phase and differences there, but mostly 2D. And for very long, as I said, this was limited to high sizes, like few microns. The obvious thing to do is to reduce the wavelength, so increase the frequency. And that will lead to frequencies in the hundreds of megahertz. And actually, that's quite tough, because there is a lot of loss. And we've heard about some of the losses in the previous talk in heat. We don't get very far in manipulating these particles. And so here, Tony has done a lot of interesting manipulations of the acoustics on the surface to enable to get down to something around 100 nanometers, which I would be happy to call nanoparticles. I mean, these are pretty small, and if you put them together, you do get plasmonic activity. So I'm not going to go too much into the details about how this works, but suffice to say that you can understand this very simply by moving the nodes around when you have these standing waves in the system. So it's rather conventional with a few tricks to enable it to go down to the below micron type of size. There's a lot of work around this in a lot of different papers, so this is just one of them. That means that now we can start to think about manipulating particles for interesting optics, and this has been done in a few different guises over the years. So a few points on localized surface plasmon resonance, so LSPR, which you can see on your left. These are surfaces with nanoparticles on them, so very simple. You just deposit nanoparticles, dry them, and that brings them together. And by bringing them together, we create plasmon interactions, and that enables us to control the way the surface responds to light. And so you can see, for example, a shift in resonance peak in absorbance when you have different sizes or different crystal lattices of these particles. So this is very well understood and very simple to make. I mean, as I say, it's just drying particles down. You can make them better by using a bit of chemistry, but very often that is the way it works. It means that it's static, right? You have a surface and you can image things on the surface by where they end up. But you can't actually move around these systems. You can move around bigger beads, as said before. And so again, this is Tony's pioneering work on moving big beads, glass beads, on the surface and using them as lenses. So I mean, we've all done this. You have a lens, a glass, particular bead. You look through it and it looks different. It looks weird, and that's how the light interact with the particle. So we have a micro lens, so a particle of a few tens of microns, few microns, that can move around the surface. And Tony has done that using the acoustics. So it's very simple because you can have the optics itself can be extremely conventional. You can have a very simple camera, and the light is focused down using the microparticle itself. So we do get to super resolution, so very far away from the resolution limit of the light itself. And so that enables to scan a surface with the beads themselves. And putting the two together, a bit of work has been done around having particles interact with the surface. So you can create the plasmon by having the particles interact with each other, but you can also create the plasmon by having a particle interact with the surface. And so this is the one at the bottom here, where we have a glass bead and a gold bead and a gold surface. And so by bringing them very close together, we have an exchange and plasmonic interaction between the surface. And so we can do single molecule analysis using the plasmon at the surface. And this, again, can be moved around. I mean, this was not done in this paper, but there is no difficulty in doing that. The trick is the fact that these beads have to be relatively small. So when we move particles around, we get the figure on the top. So this is taking the micro lens and then moving the micro lens around. Now, you can see that it feels very slow. And that's because it is just one bead with a submicron resolution, so super resolution, that moves around the surface. And you can tell that it's another D, and it's the first D for Duke. But it took so long that they only stopped at D. So it's a very complex picture. And it builds up the picture, and if you want to go faster, you randomize it, and so it goes very quickly around, and you can even use artificial intelligence to start to try and understand what the surface is telling you. But it is quite slow. You can parallelize it by having multiple particles together. But again, this is sort of limited. And it is limited to this resolution of the bead itself. So this is something that we can make a bit more work on. And we took this a slightly different approach, which uses surface acoustic waves as well. So this is a paper from the group in 2020, where we create nano lenses using the beads. So the nano lenses are created using acoustics, but the beads don't move, right? So we only move the liquid around so that we can deform the liquid, and the liquid is working as a nano lens. And so the water and the water surface is what deforms the light. So it's no longer the bead that deforms the light, it's the water itself. And so you can create these nano lenses by having a standing wave around and move that standing wave throughout the surface. Now it's a little bit tricky because it has to be very thin film. And so that means that if you use biological relevant material, water, you don't have much time because it gets a bit hot and it evaporates very quickly. And so we played a few tricks on the chemistry and used a bit of PEG and glycerol, etc., to make it work. And that enables us to scan the whole surface with a resolution which detects viruses on a surface like that, which would not be possible using the standard optics. Another way of using surface acoustic waves to look at surface plasmon resonance is that we know that we put the particles on a surface. So if you remember the previous slide, we've got these arrays of particles, and actually surface acoustic waves are deforming the surface, right? And so there was a few interesting ventures in that area where the idea was that by deforming the surface using the acoustic wave, then we can bring the particles closer or further apart from each other. So we can modulate the plasmonic effect by using the acoustic waves and the deformation of the surface. Now, in theory, in a quick theory, that sounds quite interesting, and a few people have tried. And so this is work by Kondo. So he's done a few papers on that. I mean, Kondo is again, a fantastic pioneer in surface acoustic wave. But here, he bumped on a wall, or the group bumped on the wall, in the sense that there is a scale issue. The nanoparticles are nanoparticles, so they are 20 nanometers, 30 nanometers. So it's true that in terms of height, right, the surface acoustic wave is about the right height. It's a few nanometers on the surface if you get around a watt or so of propagation. But the wavelength is huge. Right? The wavelength is hundreds of microns. So actually, although this figure shows you something going up and down, and you could see in terms of plasmonic effects that the distance between two particles here is much bigger than when it's at the bottom of the wave, right? So theoretically, if you just look at it quite quickly, then this could work. But as I said, the wavelength is huge. And so you have actually this slight variations over 2 or 3 orders of magnitude difference in terms of the nanoparticles. And so the effect that you see actually is tiny and undetectable. And so what tricked them is that the nanoparticle effect, the plasmonic effect, is also linked to temperature. And so in a similar way as the talk before, temperature plays quite an important role. And here, the temperature was the dominant effect compared to the plasmonic modulation using the acoustics and the geometry. They've further shown that this is slightly different if you're using an SH wave. So this is a transversal, right? So it goes up and down. But if you're using one on the surface, actually you can move the lattice in a much more effective way. And so you do get a little bit of difference in the plasmonics. But again, it's very, very difficult and very hard to detect. And so we are taking a completely different approach, which is similar to the work of Tony in moving microparticles, but here we're moving the plasmonic particles themselves, right? So we create clusters of particles and move them around. And so this is what this rest of the talk will talk about. So the first one is how to make the nanoparticles. And we need to make them in a way that they're not bound to the surface, which was what usually people do. And so here we take inspiration from a few papers that look at interfaces. And so we have different solvents. And when you put nanoparticles that are covered with particular surfactant, they will assemble at the interface with the two liquids. And so they form a very nice monolayer, and they self-assemble in something that's very well packed. And that can be transferred from one place to another. So quite a simple process. You do need to remove the non-biological liquids that you're using. So in this case, hexane and ethanol from the water, and you get these nice-looking nanoparticles. So at the bottom, you see the different stages from something that looks very homogeneous, and that's because the nanoparticles are everywhere, to something that looks like a cluster. This is huge. So it's we call it a monolayer, but actually in this particular case, the fact that you can see it means that it's not a monolayer. It's actually a huge amount of particles in a few different ways. But when you transfer them, they do become a nice monolayer. So I think there is a movie here to show you what I mean by things moving. Yes. So that's when you form the nanoparticles. And you can see that they constantly reorganize. That's a little bit of a surfactant fluidics that can be quite interesting and can lead to some very fancy droplets merging and breaking up. But in this case, we are just using it to assemble the nanoparticles in a cluster. Now, very often people think the cluster is the whole thing. So as I said, the cluster is not that. The cluster is tiny things within this, so you can't really see those in detail. But we now have these clusters that we can move around. So we then need to transfer them to the acoustic surface. And so to do that, there are quite a few different ways, and they're often not very practical. But there's one that works very well, which is to simply pick them up. So using capillary action, so surface tension, if you put a capillary on the surface of the particles, they are sucked into the capillary, and then you can reverse the capillary so the liquid is on top. And when you bring that down to the surface, the particles stick, the liquid doesn't go, and you get a surface of nanoparticles. This is something that was inspired from this paper at the bottom there in 2019. It works very well. There's a bit of optimization to be done, but in the end, you get particles like this. So these are a few different SEM pictures. The big one is about 200 microns. And then when we zoom in, you can see the particle lattices at 3 and 1 micron resolution, and 0.1 gives you an idea of what kind of clusters you have here. Now, this is not the same kind of cluster you will get if you do that on a surface. You can see it's not as well packed as what you can get using microfabrication. So that's because of the fact that the liquid moves around a little bit, and when you dry it in the SEM, you get these kind of cracks that form in the structure as well. But we have particles that are close together, and we have enough of them that we are able to do the surface plasmon resonant effect. So we can then put that into our acoustic device. So very simple device, 2 or 4 IDTs depending. So here is just the 2 of them, and we've got a PDMS chamber in the middle, which is open at the moment. So it's just dropping the particles in the center there. And when we put the standing waves, we get alignment of particles within the standing waves. And so you can see what I meant by the clusters are slightly different. So here we've got a scale bar at 100 microns. Remember, the big one was about 200. And so these are fairly small clusters, but it's big enough for what we want to do. And importantly, they are big enough to be manipulated by the acoustic waves, right? So we can take them and move them around. And so I think this is another movie, hopefully. Maybe not. No, that one didn't want to work. Anyway, in this movie, you would see that cluster of particles moving in the way that we don't want to write Duke, but we could have written U or G. But it does work, and it's a very simple process. There is a little bit of a trick there, because the nanoparticles often settle on the surface and stick, and we don't want that to happen. And so there's a little bit of surfactant chemistry to be used there. But it's resolved now. And so what are we able to do with that if we look at that under microscopy or LSPR? Then we do get the particles to work. So this, as a setup, is a little bit tricky, because it's only 100 nanometer particle. So if you remember the image from the micro lenses, it's a flat light that goes on. So there's no you basically see the whole surface, and your particles are only in a very small part of that. So the effect of the light, the effect of the plasmonic particles on the light is actually very small, not because the particles don't work, but because you have a lot of background of light that doesn't get affected by the particles. So you do need to focus on these particles to be able to see these differences. And so this is what these graphs show here. The shift is actually not extremely broad if you don't focus on them. So we did this for 2 different sizes, just to make sure that this is really a very good plasmonic effect. And you can see for 30 nanometers, you get a shift, and 15, you get a bigger shift. But importantly, the wavelengths are the right ones. The size of the particles usually gets you the color of the plasmonic interaction. And we've now demonstrated that we can sense, using these moving particles on the surface, a change in refractive index, which was done here very simply with a bit of salt inside the solution. And there will be a bit more detail in a conference talk by Chandresh in Meta in Japan over July, so I can't go into all the details here, so as not to plagiarize ourselves. But we have also some ideas about the surface being modified and being able to see that. So very timely, this is my conclusion. Almost, right? I've got a few interesting slides later. So we are now at a point where we can write UOG instead of Duke and show a different type of picture using plasmonics. And what we would try to do eventually is to actually go into a scanning method that's a bit faster and can be 3D. And this is inspired from work from David Phillips in Exeter, who is using optical tweezers to do just that, using mechanical particles. So he's got 2 optical tweezers here on a small pin, and he can move that around the whole surface. So you get a scanning system using a manipulated artifact. But optical tweezers are not very good at manipulating big effects or heavy effects, so it's difficult. So I will stop here for the science, and in Glasgow, we are very proud this year to inviting all of you to celebrate something, which is the 200th anniversary of Lord Kelvin. And so I just have to put these 2 or 3 slides just to remind you that this is an important year, and that if you want to follow this, it's open to everyone. So the link is there, and you'll have it in the slides. So it is an important personality of physics and other sciences, actually. But for Glasgow, very, very important indeed, because Kelvin was, and still is, the oldest and youngest student matriculated in the university. So to close, we'll do a quick quiz. Who can tell me the 2 dates? Without doing Google or ChatGPT, please. So the oldest one is sort of easy. It's 75. That's when he retired. He was still a student matriculated for a very different subject from what he was teaching. But what's the youngest date?
I'm going to go for 11.
Very close. It was 10.
Okay.
So he
guess.
matriculated as a student at 10 years old. His father was a professor in university, and he attended a few classes beyond that. I mean, not just as a childcare practicality, but he was very good at that. And with that, I just thank the clean room for all the help in device fabrication, postdocs in the lab that are now in our startup company, and the government of India for funding Chandrish's scholarship.
Thank you very much. By experience, I know that getting from Chippenham to here is not that easy. So I guess we can have a few questions, and then we can have the break. Any questions? Because everyone is ready.
So what if you couldn't make those kind of gold nanoparticles uniformly? Maybe there are 2 layers, 3 layers. Then what will influence your results?
So it depends on the application. So 2D dimension is very important if you're analyzing the surface, because the plasmonic effect actually is only up to maybe 2 or 3 nanometers away from the particles. So you need to be able to map the surface at that kind of level. And if you have a multi-layer, then actually the particles on top are no use. Right? The plasmonic effect doesn't radiate through that. But it's interesting if you want to control the plasmonics, because actually having a 2D system and a 3D system gives you a different shift in the wavelength. And so you're able to control, you have more options into what you're going to look at on the surface. Right? So you wouldn't use the 3-dimension as a way to scan the surface, because the particles on top wouldn't see anything of what happens at the bottom. But you're able to use the 3-dimensional structure as a way to control the interaction with the light.
But you mentioned that you want using Glasgow instead of Duke. That they are playing with 1 particle.
Yeah, so we play with 1 cluster. So we bring the cluster around. So the cluster, at the moment, as you've seen in the pictures, it's about 50 microns or so. I mean, it's quite big. And so we want to go a little bit lower than that, so that we can get down to a resolution of a cell. And then we can look at map cells using the nanoparticles, for example. But although the cluster is quite big, what's interesting is that you can get that resolution between the surface and the cluster to something like, as I say, a few nanometers. so molecules, right, which could be quite interesting.
Yes.
Yeah, so you mentioned that you'd managed to effectively increase the resolution beyond the sort of optical resolution of the instrument. Do you think this could also have applications in increasing resolution of things like scanning surface-enhanced Raman spectroscopy, for example?
So that is exactly it. I mean, at the moment we're doing LSPR, but you can use exactly the same principle to do SIRS. Right? So you can use the same clusters. You just have to use a different laser and wait for a lot longer, because SIRS, it takes a while. But in terms of the resolution, I just want to clarify that the resolution will be linked to the size of the cluster. And so actually it's quite large, but it's the resolution in Z that we're able to enhance a lot. So we're able to sense single molecules in that area.
Okay.
So we will be able to sense molecules at the surface compared to the bulk. So it's a bit like an enhanced turf system, if you get experience in that.
Interesting, interesting.
So if there are no more questions, thank you very much again, Julian.
My pleasure.
I think it's time for a break now. Let's have a 15 minutes break and start like 5 to 11. Thank you. Hi everyone again. If we could have you back here, we can start on time. Thank you. If anyone else, even Matthew, if he wants to come, tell them. Okay, should we start? So our next speaker is Jikai Zhang from Northumbria University, and he's going to talk on flexible surface acoustic wave technology for accelerating bacterial cellulose culture.
Okay, morning everyone, thanks for your patience. I'm Jikai from Northumbria University, and today my topic is flexible surface acoustic wave technology for both the bacterial cellulose culture. In the background here is, this is the bacterial cellulose image from the surface. So what is the cellulose? I will talk about from introduction, principle, results, and in summary. So what is cellulose? Cellulose is most common in our life, and it could be found from green plants, and also it could be produced by bacteria. So there are two different ones, one from plant, another one is from bacterial cellulose. But they have the similar formula, and but they have some difference. So the difference is in green plant, they have some different molecular size. If we want to use it, we have to do a lot deal with it and after for application. But for bacterial cellulose, we only bacterial cellulose and bacteria. What we need to do if we want to use it, we just need to kill the bacteria, then we can use it. So in bacterial cellulose is our proposal. We are using this bacteria, the name is KX, and it needs some oxygen to grow, and also the best temperature for its culture is around 30 degrees. That's very important. Here is some advantage of bacterial cellulose. It could be easy to form different shapes. It has the adjustable 3D network structure, and also have a high interconnected property, and also excellent water resistable properties, and is absolutely have good biocompatibility. Here is some application of bacterial cellulose. We can see here from biologic to food and even environment, and also we can use in electronic, and also we can use it in solar cells. So that's there are two ways we can get bacterial cellulose. Normally, in one way is the static culture method. In this way, we put culture medium and bacteria in a chamber, and after culture few days, sometimes if we want a thicker one, we need waiting a few months. After this, we collect the pellicle here, showing here. And in this pellicle, normally it will be gel-like pellicle, and it will be between the air and the liquid interface because the bacteria need oxygen to grow. So the pellicle will be grow in the upper layer or the medium. The second way is edited culture method. With similar, we put medium and bacteria inside the chamber. After this, we put this chamber on a shaker machine. So we shake it, and after a few days, we collect the pellets. So here is some example here. It could be different shapes. What's the two different of these pellicle and pellets? So for the pellicle sheet, could be more thicker and it's a hydrogel sheet. But in this way, it's more cost because if we want more thicker, we have to waiting for a long time or take some other way because we should keep the environment temperature in around 30 degrees. That means it's low rate production. But for pellicles, it could produce different size. It could be produced from 10 micrometer to 10 millimeter shapes. So that will be quicker than sheet. But there are some different with pellicle sheet, some like the low degree of polymerization and low crystallinity, and also low mechanical properties. But in this way, it's economic because we don't need too long time. We can shake a few days and collect the pellets. Here is an example to explain how is two different culture methods. We can see here from day 0 to in 48 hours, the culture speed is similar. That means in the first 2 days, they have a similar culture speed, but the difference is from 48 hours to 120 hours. We can see the agitated culture method have more produce. That means we can do some work here. Our proposal is to speed up this one. So we speed up the static culture method. So that's our proposal. How we do this? We are trying to use SAW device. As you know, we can use SAW device. It could produce some agitation streaming. So we are using the oxide film starting on the aluminum substrate. That's because it could be bendable, flexible. It could be fit for different shape of the chamber. But in this case, we are trying to only use the substrate plate as shown here. So we put a chamber on the SAW device. After the SAW device agitation and streaming, it could help the bacterial lysis, and also it could come some by supply more oxygen to the medium, and also it absolutely will come some a little bit thermal effect. That's also important to control the thermal effect. So we have different group here. We have sets at 3. The first one is control 21 degrees. We create a 21 degrees environment and without SAW device. We call it room temperature culture. The second one is a test with SAW, but we put in 20 degrees. So why we put in 20 degrees incubator? Because we have applied 0.5 watts with SAW device. Apply this power, we have method in the chamber. The medium will increase around 1 degree. So we put in 20 degrees. So after this, we can compare with the first one. The third one is we put in 30 degrees incubator. Without SAW device, that's the normal culture method, so we can compare the others. Here is some pellicle we have got from this experiment. So after we collect it, we have tried to measure the white weight first. If you see this one, the day 6, the purple is tested with the SAW device. We can say it's more than the others. And also we have tried to measure the dry weight. We can see here in the day 2 and the day. We can see here in day 2 and day 3 and day 4, the purple one not the maximum. Sorry, we can see here. The purple one not the maximum, but in 30 degrees maximum, but in day 5 and day 6, purple one is increased than the others. So if we compare with them, we can say, let's say the day 6. So if we compare with 20 degrees, it's increased around 30% than the 21 degrees, and also increased 24 degrees than the control in 30 degrees. That means our SAW device is working, is increasing the production. And also, we're trying to find out why it could be produce more bacterial cellulose. We can see here this is a CFU. We are trying to make clear how much bacteria in the pellicle. So we can see here in the day 2 and day 3, this one has a similar rate. So in Sol device and with the control 30 degrees in the first 3 days, they have the similar bacteria inside. But in day 4 and day 5, we can see the blue one here is more than the others. That's also showing us the Sol device makes some contribution. It speeds up the bacteria growth. And also after this, we have tried to measure the glucose cost here. That's showing us how much glucose we have used to produce more bacterial cellulose. We can see here in the last day, in day 5, we can see they have the similar glucose. So that means we didn't use more glucose to produce the more bacterial cellulose. That's good for us because we didn't cost too much. So here is some SEM image to support us. This one is 21 degrees culture. We can see in this is actually the bacteria only a few here, but the other two have more. If we increase the magnification, we can see more clear. Only 1, 2, 3 bacteria in this control in 21 degrees, but we can see more in the other 2 in control 30 degrees in Sol device group. That's also prove us with our Sol device we can get more bacteria in the pellicle. And also we have tried to measure how is the pellicle we got, what's the performance change. This is some AFM image. We have tried to measure the fiber size. We can see here in day 6, the test group and the control group have the similar properties, and it's shorter than this control, that's the white. For the length, we can also see day 6, control and the test is similar, and also it is also shorter than the control. So that means our Sol device didn't degrade the performance of the bacterial cellulose. We also do a lot of different work to try to find out the measurement, XRD, FTIR, and the mechanical test. So let's skip this. In summary, so our Sol device can boost the production of bacterial cellulose at room temperature. That's very important. We can do this in room temperature. So that's because of agitation and streaming of Sol device, and also is we can enhance the oxygen supply, and also it's come with some thermal effect, but we controlled thermal effect. So if we compare with Sol device group with the 30 degrees, we can see we didn't degrade any bacterial cellulose performance. And also if we compare with 20, sorry, here should be 21 degrees control group, we can do this in room temperature application. And also that means low cost. We don't need hold environment temperature. And we can do more production. That's very good for us. That means it's more economic way to produce bacterial cellulose. That's all from me. Thank you.
Thank you very much. Any questions? Yes.
These bacteria, do they have to grow at the surface, or can they be distributed as a suspension?
It's a good question. Thank you so much. But normally when it's culture, it should be between the liquid and the surface air. So if we want to control this, we should support them with culture medium. Then we talk about this, how to build different shapes. Thank you.
I have a question.
Yeah, please.
So for the powers that you mentioned, it was like 0.5 watts.
Mm-hmm.
So is there like a threshold there that if you go for higher powers,
Mm-hmm.
you basically kill the bacteria?
Yes, it's absolutely, because with high power, it will cause a high temperature. So before all this 0.5 watts, we have tried a lot of different power, from 0.02 even to 2 watts. We have to do a lot before. After this, we find out this 0.5 is the best for us.
Okay, thank you. So thank you again.
Thank you so much.
Next, we have Professor James Kwan from University of Oxford, and the title of the talk is Solid Cavitation Nuclei for Ultrasound-Enhanced Drug Delivery.
Great, yeah, thank you very much for the introduction, and thank you for inviting me to give this talk. Really, just to give an introduction of myself, since I'm not that familiar with the acoustofluidics community as much as you all are, but I did a lot of my degree, or all of my degrees in the US, all in New York, postgraduate work at Columbia, and then some postdoctoral work at University of Colorado Boulder. And there I sort of worked on studying and understanding microbubbles, which are oftentimes used as ultrasound contrast agents as well as drug delivery vehicles. I then was moved over to the UK at the University of Oxford, where I did my postdoc, and half of the work that I'll be talking about today was based on the work that I did there as a postdoc, and then eventually as part of the startup Oxonics Therapeutics, looking at solid cavitation nuclei, or developing solid cavitation nuclei for cancer therapy. I then moved to Singapore for about 4 years, actually, around when I arrived, I think it was when Dyson actually moved their headquarters to Singapore as well. But there, I'll be talking, during my work there, I will be talking about the second half, which is looking at other forms, or how can we advance these solid cavitation nuclei to address other diseases, and in particular, peripheral artery disease. And then in 2020, I came back, and now our lab is sort of expanded. Half of our lab is continuing this idea of looking towards using ultrasound to enhance therapies, and the other half is sort of going back to my roots as a chemical engineer and looking at topics such as sonochemistry. Right, so why cancer and why peripheral artery disease? Well, they actually have a fairly common challenge. Now, if we look at various therapeutic routes for cancer, you have a wide range of different therapies, ranging from small molecular chemotherapeutics to antibody therapy to viral vectors, maybe some classical vesicles. But what they commonly fall short of is the ability to treat the entirety of the tumor. So here you can see, irrespective of the cancer type, irrespective of the therapeutic, the vast majority of the circulating dose actually doesn't even reach the tumor. Most of it circulates. I think it's around 1 to 2% actually enters the tumor. And of that 1 to 2%, they only stay within the blood vessels of the tumor. They don't tend to diffuse out for various reasons. So even though you can deliver the drug, it doesn't necessarily reach the entirety of the tumor, which is a key challenge. And similarly for peripheral artery disease, whereby you can, although, well, what peripheral artery disease is effectively an occlusion of your peripheral arteries, usually of some sort of plaque-like material. Treatment of peripheral artery disease is actually fairly straightforward. Most vascular surgeons will go in with a catheter with a balloon on it, and they just push all that junk right up against the arterial wall. That's not a challenge. In fact, and that plaque won't develop for another 30, 40 years, because it probably took 30, 40 years to develop. The issue is for a substantial population of people treated with this angioplasty is that the muscle cells in the artery itself try to remodel themselves to sort of heal the area, and it can't stop healing. So effectively, the muscle cells keep growing and growing and growing, and within 1 year, the muscle cells grow all the way into the lumen of the vessel, occluding it once again. And this is a real challenge, because you can't just simply open a balloon and do it again, because the muscle cells will grow within a couple of months. And there's only so many times you can go through this balloon angioplasty before they effectively either bypass the entire vessel or just amputate. And whilst cancer, I think, is very obviously life-threatening, it's less clear why this issue of restenosis, or this reocclusion of the artery, is so life-threatening. And it's because many of the patients that undergo this process are already quite ill. Losing a limb, although is not immediately life-threatening, is such a loss of quality of life that most patients don't survive another 5 years after that. There's issues with chronic wound infections and so on and so forth. And most of these patients are diabetic. So the challenges with PAD is actually drastically on the rise, even though the acute effects aren't as evident. So yeah, effectively, because of the inability to actually treat the region of where the disease is going, so in the case of cancer, the entire tumor, and in the case of peripheral artery disease, the inability to actually deliver the drugs to the arterial wall for very long periods of time without causing other systemic effects, there remains a lack in any sort of platform to treat these diseases. And so what we propose is that maybe ultrasound might provide a common solution for this. And the general theory behind this, the guiding principle, is that we would inject some form of drug delivery vehicle that will trap a bit of gas. And in the presence of the co-localization of these particles and in an acoustic field, you'll nucleate a bubble, which will then oscillate. That forms these microstreaming patterns, or rather just generally mechanical effects of cavitation, be it in some cases shock waves, but ideally sort of these streaming patterns that facilitate the convective action that promotes the delivery of any co-injected therapeutic, for example, like a chemotherapy, or any that are directly loaded onto the particle. They get pushed into the lesion at the site of where the ultrasound is. And then you can turn the system off, and these particles, in certain instances, can reside inside the lesion for days to weeks to months, depending on how you design the vehicle, where they slowly elute a therapeutic over time and not having to expose the entire body of that therapy. Now, there are many different types of cavitation nuclei. And like I said, during my earlier degrees or my earlier time in the US, we looked at engineering these microbubbles. These are actually just mostly gas inclusions that are then stabilized by a lipid shell. And the reason why you need a lipid shell is that many of us probably have experienced that if I were to make bubbles of any sort, in this case just shaking a bottle of water, the bubbles form, but nature wants to work against us. It does not like these sort of heterogeneities in the liquid, so you'll get lots of rapid phase separation, either by buoyancy and then interaction with an interface, or indeed by just sort of an Epstein-Plesset style gas diffusion out of the bubble. So we can sort of load the surface with a lipid, and that actually helps stabilize the bubble against any perturbations in the surrounding media. So in this case, I switched from a liquid saturated with sulfur hexafluoride to one saturated with air. And so you get the sort of, to mimic the behavior of a microbubble transitioning from its, where it was created inside of the body. And so now we've extended the duration of time on the orders of hundreds of seconds, but actually if you inject bubbles, they can go sustain inside the body for minutes to tens of minutes. Now, microbubbles are great. I mean, there's decades of literature on this now. You can do all sorts of interesting surface chemistry to try and load drugs onto it, and you can play around with the gas composition, but they do fall short in a number of areas. One, they get destroyed in these acoustic fields when you're trying to do delivery. So if you're trying to sustain delivery for a month, you're really going to have to design your system very carefully. Also, the amount you can load onto the surface of the bubble is quite limited because you're effective. If it's a hydrophobic system, you're kind of stuck at this thin layer here. People have moved away from this by creating interesting ways of tethering and all sorts of other tricks. But our approach is perhaps instead of trying to include gas onto the entirety of the subject, we kind of took inspiration from sort of champagne flutes or indeed glasses, whereby actually you can nucleate lots of bubbles quite consistently, not by virtue of there being tons of gas in bubble form throughout the whole liquid, but by virtue of there being a single defect on the solid substrate. And these solid substrates, or rather these defects on the solid substrates, trap a minute amount of gas, very small. In fact, it's very hard to, anyone who works in sort of clean rooms knows, it's very difficult to remove all gas defects on the surface of a given system. But so here, in this case, rather than having obviously the entirety of the champagne flute, we then make these nanoparticles or microparticles that are laden with these surface crevices, or in this case, a single cavity. And then that, by its very virtue of being a defect, will trap some amount of gas. And because it's now a solid, we can have all sorts of fun playing around with the various types of substrates that we're using, coatings, if indeed. We can go from polymers, metals, metal oxides. And really, we're trying to just focus on how do we nucleate cavitation from this. And like I said earlier, I'm focusing, although my more recent work, part of my recent work is looking at metals and metal oxides as catalysts. Where in the context for this talk, we're going to focus on two structures, one a nanocup for cancer therapy, and then one a multi-cavity microparticle for peripheral artery disease. So for using these nanocups, these are what the nanocups actually look like under a transmission electron microscopy image. One of their key benefits is they are very well defined in shape. They're quite uniform in size in the way we make them. the challenge that, the reason why we're looking at such small structures for cancer therapy is that if you look at a tumor, the actual vessel into the tumor, the blood vessels that feed into the tumor are quite tortuous. They're very small and actually quite chaotic. I mean, you have vessels that just go nowhere. You have vessels that have no ends that extend outside of the tumor. And so as a result, large structures like microbubbles don't tend to make their way into the tumor or deep into it. They tend to stay around the periphery that's well perfused. But the challenging bit of treating the cancer isn't that well perfused area, it's the tumor core, and how do we get into that tumor core. So nanoparticles have found their way closer to that tumor core, and then the thought is by using ultrasound you can penetrate more uniformly throughout. So we hypothesized in this early work that by trapping gas on the surface, you can, if you don't supply enough energy, acoustic energy, then these bubbles will just sort of oscillate within the cavity. They don't tend to get pulled out. They'll sort of stay trapped or pinned to the system. But with sufficient amount of ultrasound, you can pull the bubble off of the cavity, and then eventually you can get this sort of inertial growth and collapse. And then these bubbles will then persist for as long as the acoustic field is present. We spent a lot of time working with the physics of fluids group at the University of Twente in Enschede in the Netherlands, actually trying to catch these and image these and then match them to some models that I developed. So here's a video of a bubble being nucleated from one of these nanocups, or perhaps a cluster of these nanocups. And what we can see is that, okay, you get this nice spherical expansion collapse in the very first cycle that it activates, and then afterwards it's quite inertial. I've taken hours and hours and hours of videos, hundreds of videos, and I've never seen two bubbles ever behave similarly post that first inertial collapse. So it's quite a chaotic system, in fact, fairly unpredictable. But from there, a lot of that work we spent looking at actually delivering. So beyond just understanding the physics of the system, we started looking at, can we actually deliver the ability to enhance transport into a cancerous tumor. So with these mouse models, what we've shown is that if you inject a fairly hard to deliver drug therapeutic, in this case an antibody treatment for cancer here tagged in green, so this is just a fluorescent antibody. If you don't apply any ultrasound and you just have particles and antibodies floating around, then here you can see, or the contrast isn't that great, but blue here are the cancer cells, red are blood vessels. You effectively see little to no green. Of course, I've taken a small subsection of an entire slice of a tumor, but you'll have to take my word for it or go to the paper to see the entire representative tumor slice, to see that is fairly true across the entirety of the tumor that we sampled. But in the presence of ultrasound and our particles, what we found is that you can see the green blood vessels, you can see all the cancer cells, and there's, the red blood vessels, and then in green you can see tons of antibodies sort of flooding all around this sort of extracellular space. And this was true throughout the entirety of the tumor slice and the tumors that we sectioned. And just to highlight, as this work was being developed, I was starting to transition away from my postdoc position and joined Acoustofluidics Therapeutics, whereby the main goal was, okay, great, you can make small amounts of this, but if you want to treat a person, you need leaders. You want to do a clinical trial, you need to scale up the production. So I predominantly worked on the scale up, but my colleagues were then working on the other bits of tech, the ultrasonic hardware, imaging, et cetera, and then they rebranded the whole thing. So we didn't call them nanocups anymore, they call them Sonotren now. So you can see now sort of scaled up, scaled up production of these Sonotren particles. And then to highlight the key differences between conventional routes using microbubbles and our Sonotren particles, you can see that if you look at some form of indicator for cavitation, in this case some kind of passive acoustic map, and they just sort of look at how intense in that map there is cavitation. With sonoview or bubbles, you can see the bolus injection, you get a spike in cavitation, and the moment the ultrasound hits, you clear those bubbles out, right? They get destroyed. So you're limiting the dose, but the intensity is quite large. So you have to constantly be re-injecting particles. But with the nanocups, you can get this nice steady perfusion. And because of that, we could see a marked increase in the percentage of injected dose correlating to that cumulative passive acoustic map magnitude. And now they've actually seen that you can get a huge increase in the actual amount of a chemotherapeutic antibody in patient, well, I guess in this case, in colorectal cancer cell lines. And now they're in phase 2, phase 3 trials that are doing very well. So I'm going to have to breeze through this a bit faster. So we thought if one cavity did really, really well, we can engineer them to have 2 or more. So we just had an n number of cavities. It doesn't really matter how many we have. But as a result, they're quite a little bit larger. But because they're larger, we can actually image them in ultrasound, conventional ultrasound imaging, and get contrast enhancement. And now these are polymers that we can engineer. We can engineer them to have varying different drug elution times, all the way up to a month. And this is critical because for peripheral artery disease, the drug actually needs to be in the peripheral artery for up to 28 days. That's the current clinical standard, let's say. All right, so here we just showed using high-intensity focused ultrasound that we could deliver the particles to the arterial wall, here labeled in red. And once they're deposited there, they will slowly elute out a drug over the course of a couple of days. And we started doing these in pigs using shock waves, lithotripsy, just because that's the smallest catheter we could use to put into a pig. What we've found is for the drug of interest, in this case sirolimus, which is an anti-proliferation drug, we saw a big increase in the amount of sirolimus in the arterial wall, and that actually was sustained across 7 days. So basically, this combination therapy was better than without the shock waving. And then now we're looking at building our own intravascular ultrasound devices coupled with these particles, looking at pig models. And effectively, we can see that, again, the particles are actually quite sticky, so they'll stick to the arterial wall naturally for some reason that we don't understand. But in the addition of ultrasound from these IVUS devices, we get a marked increase in the amount of drug present. So just in conclusion, and I know I ran a little over and I apologize, there are a lot of current unmet needs that have sort of a spatial challenge in delivering drugs, not just cancer, not just restenosis. So I encourage people, we are trying to look at other areas as well. And because we're working with solid substrates, there's a lot of design opportunities here. I've only just touched upon adding cavities and using polymers, but again, thinking about other types of materials, maybe possibly for even other types of applications. And from my experience going from academia to startup back to academia, I've recognized that there's a massive, there's a very long translational path ahead going from animals to clinical trials and beyond. So with that, I'd like to thank our current group. Actually, ironically, none of them who've worked on any of this work, but that's our most current image and all the funding that we've been supported by throughout the years. If there's any time for questions, I'd happy to take it, or we can do it offline. So thank you
very much. I guess we can have one quick question. Yes, Richard.
Yeah, so you're changing from microbubble into microparticle. So I'm just thinking that from atomic or cold wave, those two are totally opposite property. Well, is the microparticle later on you mentioned with cavity, with bubble or not?
So we've done some studies whereby if you don't dry the system to include a gas onto the surface, they will not respond acoustically. So these particles don't naturally generate, well, they might scatter some sound, but they don't generate the effect that we want, that you get that real massive contrast enhancement or the ability to deliver a drug or even measure cavitation signal. So the gas is actually quite critical. So there must be a drying phase at some point in time in the production to include the gas. And then upon resuspension, usually at the point of care, you'll just resuspend it, mix, and then inject. They'll deliver it. The nanocups are an interesting one because they're so small and the gas cavities are so small and the polymer is basically non-degradable. We've had them on the shelf for over a year and they'll always still nucleate some amount of cavitation. But earlier on they did undergo some drying step, but they can, even in a liquid, they can keep going for quite some time.
Okay,
Great.
Thank you very much again. So next we have Dr. Baixin Chen from Heriot-Watt, and the title of the talk is Modeling of Surface Acoustic Wave Interactions on a Sessile Droplet by Lattice-Boltzmann Method.
Yeah, hello. My name is Xin Chen from Harvard University, and this morning we got a lot of the work and research presented here from the lab experiment, observations on the soil interactions with the droplet, with the liquid. And I would like to talk about a little bit about the modeling work, how we could understand the mechanism and try to modeling what is the interactions exactly between the soil and the liquid. That's what I'm going to talking about. At the very beginning, I think I would like to introduce the research done by our group. I'll show you later, we do not only work with microfluidics. We try to develop some models or group models to cover a large range of the scale, to from kilometers to millimeters, even small. And we also try to study the interactions between the fluid and the fluid, or fluid, liquid, the gas, and the fluid with the solid. But then I move to the soil interactions. I think I would like to just very briefly introduce the work we did collaborate with Richard on the thermal impact. I think this morning we all interested in the thermal impact, the de-icing, whatever. We did a little bit of the lab experiment work. I just very briefly outlined that. And the details you can find from the paper we published. And then I moved to the topic of the lattice Boltzmann models we developed specific for simulate the soil interaction with the droplet on the surface. Right. So this is what we did in our group. Actually, we're more interested in some geofluid, the dynamics. The background, a lot of the things in the ocean, the pollutions, and also I think everyone heard that the CCS, all right, carbon capture and the storage. So we try to capture the CO2, and then from the power plant, then try to compress it into the supercritical states, and inject them back from where they come out, from the oil film and the natural films. But big concern is that it's possible to leak it back to the ocean, and then the local pH will change, and then they affect the animals and organisms living in the ocean. So we work with that different scales in the local ocean. We focus on the North Sea, and then down to the bubble, to the plumes and the droplet plumes. Even though finally we looked at is the possibility, the leakage of the storage, the CO2, from the sediment back to the ocean. So what is the dynamics? What is a plume might be developed? We joined with some EU and NERC project. We did some field experiment. So my work is just to develop some kind of the models to say, okay, how this mechanism it is, and to further predict the leakage possible. This is the first experiment we did in Old Ben, as the North Sea in the Scotland. We try to now deliver and release the CO2, the bubbles. The water depth is about 10 and 15, 20 meters. And then we say, okay, what is the bubbles rise up, and then CO2 might dissolve into the water, and what is the pH change, something interacted with the ocean. I don't want to spend too much time to explain that. That's some, I don't know, not working. So anyway, Can you just no, anyway, it's not quite important to. That's the models we developed. The open is over there, and then we work with about the kilometers. That's our local the models. And then there's the horizontal depth about the 20 meters. There's the vertical size, and I can show you the plumes developed. They did experiment, and then we developed the model to say what is the bubble plumes developed, and then how this the CO2 bubbles and dissolved into the water. Sorry about this, it's not working. That's the. And another experiment in the Golden Eye, that's the field area, right? That's the EU project. And then this model we developed, now in this model we didn't look at the water dynamics inside of the sediments. It's only in the water column side. And next we coupled the CO2 moving from the sediments through the sediment to the ocean. That's the plumes, the models we developed. Top side, I think, is the CO2 droplet or bubbles. I think this moment is a bubble, and the bottom, this column is how much the CO2 dissolved into the sediments. So we indicate that in the pH and the concentration. So that's another further time. We calibrated our models with the experiment data over there, and that is the simulated width. And then rest of the part is how much the gas leakage back to the ocean. Is this working? No, it's not working. Fine. Right, okay, get back to the soul. First of all, I think I don't want to spend too much time to talking about what is how the application of the soul in this industry. I think Richard this morning he gave a lot of the applications in the engineering, bioengineering, whatever. And then what we did is that we tried to understand the mechanism. So how this soul, what is the mechanism made this the fluid inside of the droplet moving or streaming and enhance the mixing inside, and how this the second part might be the pumping, okay, and how it is the further jumping into break up into the atmosphere. That's what we try to develop this model, try to understand the mechanisms. Because this morning you're talking about a lot of the thermal impact and how this temperature increased and the de-icing terms. I just a couple minutes ago I put some slides. What we did, collaborate with Richard here. That's their experiment, and then we used thermocouples and to look at what is the temperature increased inside of the droplet, one soul acting in this one side of them. Meanwhile, we put some particles inside of the droplet, and then we can monitor kind of the PIV. We see how this the streaming, the velocity developed. So that's the basic result we obtained. That we measured all the temperature distributions inside, not inside the droplet, actually the surface, because we used the thermocouples, the thermal cameras. And if we look at it, very simple thermodynamics models. Look at the droplet is our system. Okay, what is the energy they interacted with? So first one is the radiation. Your soul, the waves, the energy radiated to the droplet. And then another one is the heat transfer from the surface of the solid into the droplet. Another one, that's the third term, is maybe you got the heat transfer to the surface of the droplet to the atmosphere in the lab. And then rest of the part, this side, is all the inside. So first term is how big the energy you received, thermal energy. So you got temperature change, okay? And then you got specific heat capacity. And then that can be estimated how big this can be. And last, another two terms is the kinetic energy. You're streaming, okay, you're moving, you got some energy spent over there. We just identify how big they are. So this is our result. We see, you can see that the temperature increase and the velocity with the different, the rising of the temperatures. So that is all the energy received, absorbed inside of the droplet here. And then that's the energy radiated into the droplet. And then there's something is the heat transfer from the solid surface to the liquid droplet. Then that's finally here is the heat radiation to the droplet. We say that the kinetic energy terms it's quite relative smaller in comparison with the thermal energy. So your droplet absorbed from the soul, meaning that the energy from your soul, most of the convert to the thermal energy inside of the droplet. Streaming, that is a very small portion of the energy from the soul to drive this mixing and the fluid. Right, and next we go back to the the modeling works. Just a couple years ago, we still work collaborate with Richard, and we developed the models using the traditional CFD. What is the aim we would like to try? We just try to say, okay, what is the nonlinear term? We all knew the Navier-Stokes equation, right? The Navier-Stokes, the first term is changed with the time, and the second is the inertial force, the nonlinear term, right? And the balanced by the viscosity terms and other forces. Before this moment, the people believe that the stream inside of the flow is the streaming, is the Stokes flow. Okay, that means that nonlinear term might be not play quite important role. However, our data show that our model results. So that's the data, and this the model works. That's the model works. Okay, and that's the streaming. So we say that the nonlinear term play the key role if you try to simulate the mixing and streaming inside of the droplet. But that moment, we didn't move further with the high power, because the CFD developed, the models we developed that moment, we are not quite well to monitor the interaction between this, the droplet surface, the interfacial tension with the air. And then that is what I'm talking about today. We developed this lattice-Boltzmann model, which is quite well to handle, to predict the interactions between fluid or the gas and the liquid. That's all the governing equations the models we applied, and then say that we make some literature review, different kind of the lattice-Boltzmann models already there, but we're interested in this one, the potential one. Why we interested that? Because they can directly, in physics version, to predict or model interactions between the two fluids. Then we developed these models, that's the 3D models, this is the governing equation, and then all this term is the force terms. So there's the fluid interaction, fluid with the solid interactions, and then a new term is here, is the SOL, surface acoustic waves, this force acting to the droplet. We developed this model, and then we calibrated the models we developed with the experiment data and the analyzation results. We think the models we developed works, okay? But we still have some challenge. Means, okay, the pseudopotential lattice Boltzmann works. It's basically to predict or simulate the interactions between the two fluids. However, they got some one drawback. They generate additional, we thought that is it's an unphysically velocity at the interface. So we did some works, and then we tried to reduce that by improved the schemes. It finally works. Then we apply these models to predict the different dynamics, the streaming, the pumping, and the jetting. That's the models this experiment data is the model we developed. We calibrated with the different non-dimensional parameters. Wave number means that is the two force is the inertial force, and compare it with the interfacial tension and some other non-dimensional parameters. We say the models works, and then we still find that it's the experiment, this our predictions. We still have something different. Then we worked with this because the lattice Boltzmann we developed, we apply this, we call that is the multiple relaxed time models. The good thing for this model is that they got some relaxed metrics, and some terms is free to adjust. Then we worked with this, use some optimization methodology, and then we find, okay, this is our good options here, okay, to choose the terms, the adjusted, the relaxed time, and then we find, okay, that's the reduced, that's the physically the velocities down to over here. So finally, we got these models calibrated, and then we try to apply this model to some engineering case. First, we try to say different materials, the fluid, for use the EOS, equation of the states, and then we apply this with different angles, the droplet, and with the different sides. And finally, with the impaging, the droplet impaging with some surface, with the soul, without the soul. So what is the timing can be touched, and what is the physics, the dynamics we would like to, we're interested in. Okay, so I think I do not have too much time, but there's another applications we saw this morning. You got different ways, okay, to acting to the soul with the different directions. I can tell you that the models can predict that. Okay, well, I'm quite happy to collaborate with you guys. If you need this model to help you to design the experiment or try to understand the mechanisms, right? Okay. I leave this, the summaries over there, and thanks for.
Thank you very much.
Oh, that's my group, the student works, and the specific, no, thanks to the Richard.
Thank you very much.
Thank you.
I guess we have time for a very short question. Otherwise, we can actually move to the next talk. And you can ask Professor Chen questions during the lunchtime. Okay, thank you very much again.
You're welcome.
Next we have Jeremy Hawkins, and he is going to talk on predicting the position of nodes in a fluid on a flat plate.
Hi. Looking. Where's the screen? It's over here. So I looked at who's coming here and who's presenting today, and and realised that I've known some of the people for quite a while. I've known Hal, we did our PhDs in the same lab in the 1980s. Megan Povey, we don't actually know each other, but I've known Megan and what you've been doing since the 1990s. Oh no. And Rishi and Nick, I've only known you since the beginning of the millennium. So anyway, you're going to ask, how's it going? Well, you know. No, I'm going to take 20 minutes to tell you how it's going. So up until 1992, I was working on dielectrophoresis, and then I swapped and have been doing ultrasound since then. The good thing about dielectrophoresis is that you can use it for identifying organisms. It's great for identifying single particles, but you have to have it in a known medium. And the good thing about ultrasound is that you can use it for processing fluids. It's very good for filtering things and preparing them so that you can put it together with dielectrophoresis. You put the two together, and then you can do lots of things. You can take particles, prepare them, and so you should be able to automate all sorts of things. You should be able to identify microorganisms, do it automatically without anyone there. You should be able to do it in the environment with medical samples, do it in food, check for E. coli or whatever. Or especially with ultrasound, there's lots of fancy ways that you could process food. You could do it, everyone could have a little device in their kitchen to do something. You could have commercial reactors, you can have biodigesters to see what's going on or to actually do some of the speeding up the digestion. Biofuels, or I've used it for filtering algae. As I say, remote, you could use it for searching for life on watery moons somewhere else in the solar system. That was 1992 we thought of all these things, or most of them. Today's 2024, and there's loads of startup companies. There aren't any killer applications that I know of. No system is working on a regular basis outside the lab. I think the main reason is we forgot to tell anyone, and so we didn't get enough money. We should have told more people, we would have got more money, all those things would be working by now. There's another reason, and that's what I'm going to talk about today, that we've got some of the theory wrong. Let me have a pointer thing. So the standard idea for how ultrasound works, by the way, when I say we've got something wrong, I'm talking about ultrasound in channels. I'm not talking about dielectrophoresis. I don't know about that, or ultrasound anywhere else. And I seem to be about the only person talking about ultrasound in channels today. But the standard idea is that you form a standing wave in the channel, and it forms nodes, and particles go to the nodes. And I'm saying, no, that doesn't happen. You have a substrate, and waves come out of the substrate, and you get an interference pattern. There's no resonance in the fluid. You get an interference pattern, and nodes form at the interference pattern. So there's a resonance in the substrate, but no resonance in the fluid. I can't see the screen over there. So why, when I say it's working this way, why have we got it wrong all this time? It seems obvious that if we've got a substrate here, the nodes are going to be at the half wavelength of what's going on in the substrate, not in the fluid. But we always get the nodes at the half wavelength of the fluid. It's obvious I'm wrong, but I'm not. I don't think so. So in we were working with how these form in large systems until around 2002, and then Swedish groups, 3 Swedish groups from Thomas Lorell, Linda Johnson, and Martin Wickland changed their system from one which is more like this with a substrate at the bottom and a reflector at the top. They changed it so that now waves are going from side to side. And I've never quite understood how to model a system like that. So now I'm saying that the system is like this, but the nodes are the same as the ones in the substrate, but somehow or other they've come closer together so that they're the same as the ones in the fluid. And the reason for that is that when you put water on the substrate, the nodes in the substrate come closer together. So the mass loading onto the substrate changes where the nodes are, and then that pattern gets transferred up into the fluid, but there's no resonance in the fluid. And I'm going to show that by doing it that way, we get good agreement between the where the nodes are in the substrate and the nodes in the fluid. To do that, I had to get rid of the walls in the system because it's confusing. The sound could be coming through the walls, or it could be going up through the I'll go back. The sound could be coming into the system through the walls here, through the sides, or these walls could be transferring sound up to the top layer. So if we can get rid of them and have a system like this, then we've just got a lower layer. There's no question that sound is coming from the sides. And there's no transfer of sound up the sides. So get rid of the walls, and it makes this system easier to understand. But to get rid of the walls, we use the capillary system. Now we've got a microscope slide with something over the top of it. I'll just show you. Got a microscope slide. So I just put a bit of water on this bit of plastic. There we are. It sticks to it. That's a channel there. You can pump water in here and get it to flow out at the other end. There's nothing new about that, because that's the way that a pen works. It has liquid flowing down a nib, comes out at the end. So there's a capillary bridge down this channel here, and there's also a capillary bridge as it goes onto the paper. So capillary bridges, they're quite robust things. And also a paintbrush is a multi-channel capillary bridge, works basically in the same way. It's a bugger. I can't put any patent on it. It's been around for a while. Okay, I want to draw pictures. Basically, I want to draw pictures of sound where I show the wavefront. There's a few ways of drawing sound. You can draw it like light as a ray diagram. With a ray diagram, these arrows are the rays. The sound is going in that direction in the liquid. So here we've got a plate vibrating. Sound goes into the liquid, but the liquid has a different wavelength to the plate. Let's say it's got a smaller wavelength, and then the sound, the peaks have to match up. So this point in the wave has to match up here and here, but it's a different wavelength, so it tilts over. And then you get a leaky wave that's tilted over. And so the wave fronts are going up this way, the wave direction is in this direction. If it tilts over all the way, then the next thing is it goes back in again. And so just a little bit of the sound comes out, about half a wavelength, and goes back in again. That's called an evanescent wave. You get the same in light. And I'll come back to evanescent waves later. This type of traveling wave system has been described by Tony Huang, where he talks about standing saw waves, because he uses saw waves. I don't use saw waves, I just use plate waves or whatever, microscope slide. And instead of it traveling out, the two beams cross each other and they form nodes. So he hasn't drawn the nodes in the chamber, but there's nodes form where they cross. The trouble with that is it doesn't tell you where it starts because they're just traveling. Well, they're not traveling because it's a standing wave. So I prefer this diagram. In this diagram, we've got, it's the same thing. All of these are the same pictures. This one, this wave comes from the antinode and goes out into the liquid. And where the waves cross, you get interference. So it's the same as someone hitting some water, you get an interference pattern. At this point, it's all going out at an angle, but very close in, they go out as straight lines. And ours is close in, we're only interested in the half wavelength. This is a COMSOL picture. COMSOL shows intensity diagrams. So as I say, these are the same pictures. That's what COMSOL will give you. And this COMSOL diagram, it was made by Siddharth, who is one of Richard's PhD students a few years ago. It shows that there's sound in the substrate and there's sound in the water. And the nodes are continuous. They go from the water to the substrate. It's also continuous in the antinodes as well. Here it doesn't look continuous because it's red and black. It's just the way it's plotted. We actually did the two things separately and then joined them together. But it should be all blue here, all red here, or whatever. So it's important that it's a continuum. It can't be anything else. You can't have an interface with a sudden change. And a final way of plotting things is a displacement diagram, which looks nice. And I'll show some of that later. This one, as you can see, it shows the leaking wave. I want to point out that this type of wave is a plate wave in the plate, and this plate has got a symmetric wave. So this one is called anti-symmetric because one side goes out, the other side goes in. Here, both sides go out, so that one's symmetric. Okay, before these type of channels came along, I was working on either larger channels or half wavelength channels where we had a piezo T, some glue, stainless steel, water, stainless steel, and we were getting a standing wave in this system. And we could model this much as you'd model a piece of string. Just imagine the piece of string is made of a piezo T, glue, stainless steel, and water. And we get where the nodes are in the system. And the person doing the modeling was Helmut Novotny. And I made the system, and we got pretty identical results. So nothing happens at lots of frequencies, and then suddenly we got a good filtration result here and a good filtration result here. So we had a nice system, and then, as I said, around the turn of the millennium, Swedish people came along, turned the node round, and I didn't know how to model it anymore. Because here it should be a quarter wavelength for the reflector, but they had huge things. So going back to my capillary bridge, I'm not just going to talk about that capillary bridge. We've got a narrower capillary bridge. This is something that Sadaf has modeled in with COMSOL. And so I'll show the COMSOL pictures with this one. It happens to be upside down. It doesn't matter whether it's upside down or the right way up. You can see it sticks on, whatever. When you look at that capillary bridge, put some yeast in it, it forms 3 nodes. And this is what happens in the water. The pressure has 3 nodes again. Look in the glass, and you see those 3 nodes. So this is the microscope slide. This is the capillary bridge. I've turned it round so this sort of fits on the end. Here, the sound, obviously the sound starts in the glass and goes into the water. It can't start anywhere else. But they match. If anything, it's stronger here than it is here. And so I'm saying that we've got a standing wave, a resonance in the glass, and then a standing wave, which is just interference, not resonant, in the liquid. There's a few questions. Why does the water? Why do the nodes follow the water's edge? Why are the nodes in the same position in the water and the glass? Why does the node-node distance decrease as water depth? Decrease with water depth. I haven't told you about that one. Why is the stress 2-2? Okay, this is not pressure in the glass. This is the stress just in the direction coming out of the glass, going into the water. If you plot pressure, you don't get such a neat picture, but obviously the only part that affects the water is the part going in to the glass. Why is it greatest in the region? There's less stress here than there is in the region of the water. And why does the probability of nodes increase as the channel width decreases? I'm not going to answer those questions. I'm going to go on and say, break this into parts and then use disperse to model it. And the point of using disperse is that we can look at nodes, modes, not nodes. A mode is in a violin string. You cut it in half, you double the frequency. With 3-dimensional things, you can either have a compression mode or an antisymmetric mode. And you can see here, when you double the frequency, the length is more than half. The velocity increases with frequency for this mode, but not for that one. This is what disperse normally gives. I wanted to know what happens when you change the thickness. So I just looked at 1 megahertz, changed the thickness, and we find that these modes change like this. And then I wanted to know what happens when you change the density. These two show that. Then using this experiment, we plot the experimental results over the top of what disperse has given us for the thickness, and it fits well with the antisymmetric plate, but not with the symmetric one, or there's an outlier that may be there. It's possible that it could be doing both. That's a system with polystyrene on top. If you change it to glass on top, they also fit. If you change it to a thick layer of glass, a 1 millimeter thickness of glass, this was 50 microns of glass, then disperse and the experiment show it goes straight across. It's always at the half wavelength of water. And so if your plate is half a wavelength thick, if your top is half a wavelength thick, it doesn't matter what else you have. The nodes will be half a wavelength apart, and so that's why everyone gets half wavelengths between their nodes, because they're using thick tops or they're using thick layers of water more than around half a wavelength. If you use a thin top or you use very thin water, you get a different result, but everyone else is working in this region. This is how to see it in disperse. And there's a few other things you can see. You can, I'll show these at lunchtime. There's an experiment over there, and I'll show all those. You want me to finish, don't you? To show that if you have exactly a half wavelength or a wavelength, then clumps form instead of the lines going across. And I worked that out, how well the clumps were forming just by counting the number of clumps. And it shows that with a non-reflective top, the node is at the reflector. With a reflective top, the node is down from the reflector. You want me to finish? I'm going.
So thank you very much, Jeremy. Jeremy is always very kind to bring experimental setups and like teach in hands. So please do visit Jeremy's experimental setup over there. Any questions? I guess if you have any questions, we can actually ask Jeremy there during the launch, after the launch. A few points before we move to the launch. So feel free to, for the launch, I guess if we can take a group photo like last year. I guess last year we took a good photo. So this year, I guess 5 minutes to 1, we can take a photo. It's sunny outside, so we can take a photo outside together. And we can start a second round at 1. Thank you.
Hello, everyone. Welcome back this afternoon session. So let's move on. The second talk is from Dr. Despina Mocho from University of Bath. Sorry for my pronunciation.
No, that's okay. It's not an easy name. I will try to stay within time as much as possible. So first of all, thank you very much for the invitation. It's nice to be here. And thank you very much for inviting me in an Acoustofluidics conference when I do something marginally close to you, but I think we will see how this all fits in. So basically, my name is Despina Mosco. I am a senior lecturer in electronic and electrical engineering at the University of Bath. And I will talk to you about what we call a lab on and what some colleagues have started calling in a printed circuit board. So I will tell you a few things about what lab on chip is in general, since you are all microfluidics people. I'm sure you know what lab on chip is, but at least my electronics view on it. What are labs on printed circuit boards? The work that we did on the coronavirus, the recent outbreak, other projects that we're running, like wearables, diagnosis for sepsis, some work with cancer management, and other projects that actually also include an acoustofluidic device. So what is lab on chip? From my perspective, microfluidics have always been a component of integrated lab on chip devices. So coming again from a pure electronic engineering background, it's the equivalent of the integrated circuit for electronics. So bringing together all the different microfluidic, electronic, micromanipulation components into one complete microsystem that can do biochemical analysis. Why are we interested in lab-on-chip devices? Because we believe that they are they could transform basically the way that we do biochemical analysis in a variety of different areas. Most colleagues, including myself, have focused a lot on biomedical diagnostics. But of course, there are other very important applications like environmental monitoring, defense, food safety. So imagine the impact of having a biochemical laboratory in your hand instead of sending your sample somewhere. So this is what lab-on-chip is trying to do. Now, components of lab-on-chip devices, microfluidics, are channels, separation devices, micro pumps to manipulate the liquid, micro mixers to make the reactions happen, and of course, what for me has always been the core of a lab-on-chip device, which is the sensor. So the quantification of the analyte that we are interested in analyzing for its application. So I told you the components. I told you that in my perspective, lab-on-chip is basically an integrated microsystem. So how do we make this microsystem? The reality is that we don't have a consensus. So different groups use different technologies. So one of the biggest ones, and the prevailing, I would tell you, for a very long time, and actually the one that I started working on, is silicon-based, so CMOS technology. Why? Because we had the laboratories, we were doing electronics. It was quite easy, actually, to shift the existing manufacturing and microfabrication into lab-on-chip devices. Semiconductor fabrication techniques are very well known. They have been used for a very long time for many applications. We can have sophisticated electronics. As you all know, it's a billion-dollar worth industry, or a lot of commercialized components. We can integrate microfluidics on them. Here you see the ion torrent device that actually has microfluidics integrated on them. However, when you want to upscale and want to go into low-cost devices at the mass manufacturing scale, how many centimeter-wide devices can you fit on a single wafer? 5, 10, not 1,000. This means that the overall cost of its device can never be as low as we might want in lab-on-chip devices. Glass has, of course, was one of the first technologies that was explored. Very well-known material, transparent, biocompatible. Again, this is not the cheapest technology in the world. And of course, it is not straightforward to build electronics on it. Polymers have dominated. You must know you are all working on microfluidics. Why? Because they're cost-effective. You can do them in any lab. But if you want to have electronics in there, to have quantification, for example, for a sensor, how do you put them there in an upscalable fashion? Because in a lab, we can prototype whatever we want. But as soon as we want to transfer this into an upscalable process that we can deploy in mass manufacturing, this is not straightforward. Paper has dominated a lot. Why? Because, of course, this is cost-effective. We can print things on paper. We can filter things on paper. We can see the results with colorimetry of any analysis on the paper itself. Again, the question for me is, how do you put electronics there? You can print some electronics, but this is still in its infancy. It's not really commercially good to go. So a lot of problems and no solutions. What I found interesting, I think by serendipity throughout my career, has been the possibility of using existing factories from the beginning, from prototyping. So what if we use printed circuit boards? This idea was, I can't take credit for it because it was first suggested in the 90s when the first lab-on-chip devices were stipulated. But at that point, integration was not actually at the forefront. So people were looking to prove more fundamental properties in microfluidics. So basically, they moved on to basically polymers and plastics. Recently, we started thinking about how can we transition now lab-on-chip devices into real-life deployment. So integration became a bigger focus, let's say. So PCBs, from the integration perspective, I think they have some unique advantages. So the factories are there. We don't need to think about it. Where are we going to manufacture them, and are they going to be low cost? They exist around the world. In terms of microfabrication capabilities, we have converged. So basically, the dimensions that we are looking for in conventional lab-on-chip devices are micrometer scale, which is actually what printed circuit board technology can achieve at the moment, quite routinely. And in terms of integrating electronics, it's obvious because they are built for electronics. So it's an obvious transition. Now, I started working on this through chance, basically, with my first handmade printed circuit boards, basically not within the agenda of creating them with printed circuit board technology, because we were trying to make a fast PCR device, and the printed circuit boards were there, and they were the cheapest option. We had limited resources as a lab, so we thought, why don't we just make a micro heater on a flexible PCB with the copper that was there, and heat up the sample, make some channels, and see if it would work, right? It seemed pretty simple. It took me 2 years, of course, to make it work, because nothing is as simple as you think it might be. In the end, it worked, of course. And if you get all the technical details to work, I basically reinvented by myself the PCB fabrication process because I was not familiar with it, but basically it worked. And actually, apart from the fact that we were able to do rapid PCR at that point for bacterial detection in food, in dairy products, we also thought that maybe we can take it a step further now and see if we can integrate also some sensors in here. So over here, I'm sorry, I don't have the Dyson broomstick with me, but basically over here you see a silicon sensor that we try to integrate. Okay, thank you. So there is a silicon chip here doing actually real-time detection of the amplification product. The difficulty here is basically that the PCB is a rigid FR4 device, and silicon is a different material. How do you make this fluidically tight? It did work for publication. I made it work manually, but I wouldn't recommend it to anyone for upscalable production because it's not something that can be done. It's something that can be done only with a PhD student, basically carefully sealing everything so that there are no leakages. So at that point, I was thinking, this is really cool, but how can we move beyond that, right? And this is where I started looking into publications of, okay, if we can have the amplification device there, can we have the sensing there on the same seamless integration on a printed circuit board? That was not me. So actually, other people have done that. They had started showing electrochemical detection on printed circuit board traces, which actually are routinely plated by gold or even silver commercially, right? So people have been using that for sensing. And this is exactly the point when my previous PI invited me in Southampton, because coincidentally, he had the same idea. What if we could use printed circuit boards to do lab-on-chip devices? And coincidentally, we found each other, and he told me, you know more than me, so maybe you should come and you should do that in Southampton, where we can actually work with an industry instead of you doing everything with your hands, which was actually correct. So I worked on a project based aiming for ELISA analysis. This is actually protein quantification analysis for many different applications. In this case, we were aiming for tuberculosis. So quantification of interferon gamma, which is a biomarker, protein biomarker associated with tuberculosis. And the whole idea was to see if we can work with Newbury Electronics, normal, I wouldn't tell you anything exceptional, PCB manufacturer to make the whole system. So I came up with an approach of having a 3-layer sensing device with integrated microfluidics, as you see, using only what was available within the industry. I designed this microchip, which had integrated, of course, also the electrochemical biosensors, and also integrated because this technology allows us basically to design lab-on-chip devices the same way that we design integrated circuits. So here we could have 6 independent channels, where one of it could be used for a positive control and one of it for a negative control. Now, here is the testing, the electrochemical testing of the device. You see here the final device. We got the 3 different layers from Newbury Electronics, and I manually put them all together myself because I wanted to do some pre-processing on the reference electrodes, working, of course, with Hao in the electrochemical detection part. And what we saw after testing with clinical samples was that indeed we could have similar results with a conventional ELISA, of course at a fraction of the time, okay? So the analysis here took, after the immobilization of the primary antibody, I will tell you 10 minutes in total. The normal ELISA that I did in the hospital in Charing Cross took, I mean, including the incubation, I would tell you a day. So in terms of analysis, the improvement was radical. However, you see here that the error bar in our case was huge. I was certain, I knew, of course, what this was attributed to, and I always thought it was because of the quality of the plating that we had on the electrodes, which had some impurities. And at that exact point, this is where I moved to Bath, trying to exploit this technology further, because I thought it had legs. And I wanted to see what it can do beyond that. First of all, if we can understand why we have these large errors when using what seemed to be obvious technology, and then see what else can we use it for. Can we expand it to make it kind of a standard? So in Bath, the first attempts that we did were for nucleic acid sensing on these devices. And we exploited, because I thought that the plating was actually a critical factor, we exploited 2 different commercially available gold platings. And indeed, we saw that these were the issue here. We got very low limits of detection. We went down to 57 femtomolars for nucleic acid detection. And indeed, we saw systematically that the electrode surface and the quality of the plating was actually one of the most critical factors. Then we tried to see what else can we do. And at that point, I was working with one of my first PhD students on sepsis, so quantifying protein biomarkers using, again, the same printed circuit board technology. In parallel with our work, some colleagues in the Vinci Institute were also working on sepsis diagnostics. We had overlapping a few biomarkers and a few that were special for them. So we did a very nice collaboration there, and actually we got, again, results to work. In parallel, I had a lot of colleagues from around the world who were asking me, if your electrodes are working that well, can you give me some? And I started giving them away. My students then stopped me because they told me I should sell them. I should not just be giving them. And this is how Biotip started, so my first startup, basically just to sell the electrodes that we had worked out the details on how to make them work well for electrochemical detection. And all of a sudden, as soon as we started selling them, there was competition from other groups, which was quite a surprise again for me. But still, I mean, it started to become a thing. In parallel, of course, we carried on with our academic work and I always wanted to explore if we can make this a standard. So the way that we design electronic boards now, we have design rules. They are all the same across all the factories. You can design in the same way wherever you are on the planet. Can we do the same things for lab and PCB devices? So with Sotiris here, we started working on creating an example of, can we have libraries for lab and PCB devices, microfluidic channels, detectors. So can this become a thing, a standard? We made an example of it, right? And we actually have engaged a lot with the industry, with Altium. I was actually in one of their conferences. There are a lot of PCB factories now across Europe and internationally that are interested in offering this as a service. And it is up to us basically to expand and the manpower that we have to expand further. Now, in between all of this business, the pandemic happened. And I think everyone's life changed, including mine and my group's, because all of a sudden, the diagnostic testing was at the center of everyone's life. Everyone needed to be tested. Now, for those of you who are not familiar, there are two types of testing we can do. Molecular testing, so the PCR swab test that I'm assuming most of you have done more than one time, quite annoying, but anyway, this was the standard for this detection too. Antibody and antigen testing, which is a different technology from PCR testing, so it's not molecular. At that point, there was a huge mess. Many people calling many people to start projects on how we can improve testing and stuff. I was also involved in a lot of this mess. But out of all of this mess, we thought that maybe we can exploit and translate the work that we do, not start something new. But considering that we have already done work on molecular testing and rapid amplification, maybe we could help and maybe we could exploit it further. So we managed to find a little bit of funding, working together, of course, with the University of Glasgow and with Julian and John, who gave us their rapid LAMP amplification protocol for COVID detection, and tried to see if we can put it in our platform and make it work. In parallel, my company was involved in another mess with rapid testing on lateral flow technology, which was another branch, let's say, of our work, which took a different path and was relatively successful, I would tell you, as a commercial venture. Now, I will focus more on what I always thought was more important, which is basically the molecular testing. So what we designed in the end is a portable molecular test, so the equivalent of PCR, because it's actually a LAMP test, it's not a PCR test, but it is the equivalent of a PCR test, which is portable. And actually, after a lot of work from Sotiris, basically, and everyone else involved in the team in a very turbulent time, what we managed to do is basically integrate the thermal lysis, so nasopharyngeal swab to result on your smartphone within 3 minutes without any sample preprocessing, which I have to tell you was a surprise for us too. We went step by step, expecting somewhere to fail, and we didn't, which was really, really a surprise. Also, the time was a surprise. I never thought we would be that fast. But basically, what this microchip does, here in the beginning, you have the thermal lysis of the virus within 1.5 minutes. And directly after that, without any other sample preparation, you have the LAMP amplification step. The reason why you see 2 of these channels is because we have the control on the other side running in parallel. And in the end of the system, we have an off-the-shelf fluorescence detection. Again, nothing fancy, nothing to elaborate, completely off-the-shelf, in continuous flow, measuring the amplified sample. And of course, you see your result in a custom-made smartphone app on the spot. Here you see one of the calibration curves that we have. We did clinical testing with real patient nasopharyngeal swabs, and actually we had a similar performance to the conventional PCR test. We also tried wastewater. Of course, you can find all of the details in the published work. So what we did find was that with wastewater, of course, you needed a lot more sample preparation. So you cannot just flush them through the same way that we do with nasopharyngeal swabs. And of course, we're trying to expand now this work for other pathogens. We try also to understand why on earth it is working so well, because this can lead us into designing better systems in the future. And in parallel, I will go very quickly because I think I'm running out of time, as Julian predicted very accurately. In parallel with all of this work, we have been working with wearables, so with flexible printed circuit boards to see if we can create patches for different applications. So with glucose quantification, we have worked with enzymatic sensors and non-enzymatic sensors, all with the same technology, everything commercially fabricated, with very good results. With Sotiris, we tried to see if we can make graphene field effect devices on the printed circuit boards themselves. They actually worked. We tried to detect whole bacteria with impedance with our collaborators in India, in Mumbai. It worked. Then, of course, we have a very big activity on water diagnostics. We recently got awarded in Bath Center of Excellence for Water Technology, 13 million, if I'm not mistaken. I'm not the PI, so I'm not taking credit for it, but I am, I would say, a part of it, a big part of it. We're kicking off next month. So a lot of work on water quality diagnosis. The most interesting application for me was in aerospace, which is something I had never imagined in my life. So basically, there was interest from Airbus in assessing with a lab-on-chip device the quality of fuel in the tank, which apparently is a big problem and has not been addressed so far. The big advantage is on lab-on-PCB there. This project has been ongoing now for 5 years, and we're still working on it, actually, again, with Sotiris. The biggest advantage the lab-on-PCB technology has here is actually the standardization. So our devices come from the factory. The factory is accredited for aerospace. So basically, the Airbus can take them and put them on the plane. That is a huge advantage, because nothing can go on an airplane unless it is manufactured in an accredited fashion. So still working on that, very good results. Have not published anything yet, because basically we have all the commercial implications here. Working a little bit with organ-on-chip devices. I just want to finish without taking too much time with the acoustofluidic aspect. So I'm not an acoustofluidics expert, but while I was speaking about what I do, I think 6 years ago, in a conference, I met with Chris Young from Cardiff, who is an acoustofluidics expert. And he actually told me, do you think what you do would be applicable in acoustofluidics? And I'm like, I don't know anything about acoustofluidics, but why don't we explore? Why? What is the problem with acoustofluidics? And he told me that basically the big problem was lithium niobate. So basically the substrate that a lot of you use to produce acoustic waves is very expensive and quite difficult to source. So he told me, is there a possibility, because at the moment the electrodes are manufactured directly on this lithium niobate wafer, is there a possibility to separate them and have the electrodes on the PCB and lithium niobate as a reusable component? We explored that and it worked. You can find again all of the details in the published work, because I don't want to take more of the time that I have already taken. And we successfully did with Chris droplet streaming, and actually also patterned lung cancer cells using acoustic tweezers. So it is working and it is detachable. So you can reuse the lithium niobate substrate. And now, summing up, we have been using our technology for a lot of different applications, because this is what we want to show, that it is a platform way of making lab-on-chip devices, of course, with limitations and with advantages. One of the biggest killer applications, let's say literally killer, is basically the COVID work that we did, which showed what are the capabilities of this technology. It also showed why engineering is required. Additionally to fundamental science and medical science, we need also good practical engineering to get this technology out there. What we offer with Lab-on-PCB is cost-effective manufacturing, practical right now, within the UK, not in Taiwan. So here, and the Lab-on-PCB possibility offers many different process options, many different material options. We have showed prototypes for various different applications. It is compatible with what we do, so we keep pursuing this approach because we think it is a way forward for the field. Thank you very much. I was not too much over time, but I'm happy to take it.
Thank you very much. So due to time limitation, we only have one short question. So anyone got question? Oh, because it's too short, so nobody got. Okay, maybe I ask. So I know that the PCB sounds like from cheap, low-cost point of view is good. But if you consider about sensitivity or precision, because the PCB is quite rough, copper, then it's very difficult to make into a high performance like silicon-based, right?
Yes, and I think that is the limitation. I don't think personally there is one solution that fits everything. So if you want to do nanopore sensing, you would not do it on a PCB. I would not do it on a PCB. I think this is not the right way. Or if you want to do precise optical detection, single molecule detection, I think this is the wrong way to do it, right? But if you want to do, so I think we need to think more of finding the right tool and the right technology for the application.
Yeah, that's true. Okay, thank you very much. So now we need to move on to the next talk from Professor Hywel Morgan from Southampton University. Yeah, his talk is from smartphones to diagnosis.
Yep.
Yeah, that's great.
Good afternoon. It's not working. That's a good
It was working earlier. I have a lot of videos on here, and over the decades, I've learned not to. But it's not connecting now.
Oh, so you use VR. Maybe it's control from there.
Is there a loose connection? No, that.
Here.
So I'm going to talk about, here we go, a project that started originally when I worked with Sharp, the big electronics company that makes displays. I'll put this down. And they have a research lab in Oxford, and I had a Royal Society industry fellowship to work with Sharp. And you'll see what I did during that fellowship as the talk progresses. So I'm going to talk about digital microfluidics. You've heard a lot about acoustics, so moving droplets, moving liquids, moving particles, and so forth. I've spent my career moving and analyzing cells and liquids with electric fields. And so what we want to get away from really is this complicated image, which everybody now has seen, which is the chip in the lab into a system where we can move liquids and particles remotely. And to do that, we use physics of electrowetting or dielectric, which has been known about, or originally goes back to Lippmann. But the concept, the simple concept that's shown in this diagram here of having the green bit, which is the dielectric on top of your conductor, was only invented in the 1990s. It's not so long ago when you think about it. And basically you have a circuit, so you have a conductor, which is the base there, very, very thin dielectric, charges, fields dropped across the dielectric. A liquid, which is a conducting aqueous liquid, and then an electrode in the top, which is your circuit. And if you do that, you can move droplets by applying a field. And in a kind of simple way, the contact angle changes. That's not actually what happens. What happens is that the energy changes. And this is the equation here. You can see the energy half CV squared in there. That's the capacitance in the system that changes. And so there's no laser on there. No, it's fine. If you can move a droplet in that way, you can do lots of things with it. For example, Philips developed a lens, an infinitely variable lens, which is now sold by, I forget, one of the big optics companies anyway. But you begin to think then about making lots of individual electrodes. And if you apply a voltage to each of those electrodes, you can begin to move a drop from electrode A to electrode B to electrode C to electrode D and so forth. Right? So you can do what's called Is it where I'm standing, maybe? Maybe it is where I'm standing. I'll stay here. Something called digital microfluidics. So this cartoon here shows the concept of having multiple inputs, along the X and Y axes, right? You can route fluids in. I can see it on the screen now, so it's fine. And then you can begin to do all these sort of ideas that you need, which are in a miniature system, which are dispensing fluids, splitting fluids, merging fluids, all the kind of stuff you do in a lab with a pipette. And this is not a new technology. In fact, there was 10 years ago, Science Translational Medicine entire volume about digital microfluidics and so forth. But the biggest issue really is when you think about having discrete electrodes, like in this image here, there are only so many wires you can connect to a chip. If you've got 64 electrodes, you have 64 wires, 100 electrodes, and it gets a bit out of control. Now, I'll have to stand still. In that first cartoon I showed you, there was a wire in the top of the droplet. But if you look at a typical, what we call passive electrowetting or digital microfluidic system, the structure is like this. You've got a conductor on the top, which is transparent glass, but it's indium tin oxide coated. It's just like the front screen of your iPhone. On the bottom, you've got another electrode, but there are multiple of these, let's say 50 or 100 electrodes, right? Insulator, hydrophobic layer to make the contact angle very high, and then either oil or air in which you have a droplet of water. So you can do it in air, you can do it in oil. It's a low dielectric constant, and the water is high dielectric constant. And then if you apply a voltage to these electrodes, so you can move the droplet, right? So you apply a voltage, droplet moves. That's not scalable. So what we were doing with Sharp, this was 7 or 8 years ago now, was thinking, how can we scale this up? And what we do is we use active matrix technology, thin film transistor technology, just like you've got in your phone, which I've left on the chair. You've all got these in your displays on your phones, right? So the displays have got millions of individual pixels, each of which are controlled by a transistor, thin film transistor. It's basically a switch. It's a low frequency switch. So I take away the electrodes that were on the bottom, and I put in there a switch, which is a thin film transistor switch. And then I can make a device which is programmable. And when I give this talk to students, I say to them, how many of you have actually put your iPhone under a microscope? How many of you put an iPhone under a microscope and had a look at it? What you can see are individual pixels, right? And it's quite interesting. If you do that, and if you've never done it, it's fun to do it, you see this. So these are the individual pixels, the RGB pixels that control the liquid crystals, that control the display. And so what Sharp did, we worked with Sharp to do this, was to take this technology, redesign it, manufacture it, in fact, in the iPhone fab in Tenrin, Japan, and shrink it down to make this, what's in this image here, this small, fully programmable electrowetting digital microfluidic device with hundreds of thousands of electrodes. And the person who did this in Sharp is pictured there. That's Ben Hadwin. He was the circuit designer that came up with this. So the devices we made, you can see the size there, 36 by 20-something millimeters in size. They're quite small. And that's silicon processed on glass, just like the displays that you've got in your iPhones. So that one, in fact, had 16,800 individual electrodes or pixels. And in each of those, if you zoom in pixels, we have lots of circuitry. And the individual pixel is about 200 microns in size, and it generates the voltage that causes the electrowetting to occur. But it also has a circuit in there which measures the capacitance above. And if you can do that, you can determine then whether you've got oil there or whether you've got water there. It's a very simple sensor, but it's about as good as you can do with TFTs. But that's quite interesting because instead of looking down a microscope to see where your images are, sorry, where your liquids are, you can create an image from the electrical capacitance readout. And so it's an AC voltage driven system, 20 volts. We have to keep the voltage low because these dielectrics are thin and you can't go to high voltages with TFTs anyway. And we have this sensor. And the image on the right there shows the electrical readout from each of those individual pixels, color-coded. The image on the left shows, looking down a microscope, pictures of a dog bone-shaped drop of liquid. And the correlation is excellent. So I'm now going to show you my first video. And so what we're doing here is looking down the microscope, optical microscope, at this device. And in the first image, I said these are droplets. In fact, they're not really droplets. They're more like discs because they're moving between two sheets of glass. If I run the video, you can see all we're doing, this is in real time, is programming this device, just like creating an image, to move these droplets around. This is the readout from the capacitive sensors. You can just click and drag drops around at a computer control. So click that one there and move it to there. And the computer does this, generates the image and moves the droplet. This is quite long. I may stop this in a minute. You can merge droplets. You probably all know in microfluidics, it's very difficult to mix. So you can create these programmable sort of stretching, kneading type things on the device to mix droplet. This is showing dispensing liquids. On the right is the sensor output. On the left is the optical output. Here we can see how we can split droplets. So we can split into a single pixel, single droplet. The size of these droplets is between 10 and 500 nanoliters, so they're quite small. This is a single array droplet splitting. Each electrode, I should have said, is about 200 microns. And the gap between the 2 bits of ITO is about 150 microns. It gives you an idea of the scale. And it's difficult to see this, but what we're doing here is going click, 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 click with the mouse, and the droplets are following the mouse clicks. And I'm going to stop there because in the interest of time. And we use this for a number of things. This video here shows an assay which we developed to determine whether or not a microbial infection carries genes against antimicrobial resistance. Right? So these genes on the top, NDM1, KPC, and CTXM, they're genes that say that this bug is resistant to meropenem or something. And you can do that on this device, and I'll just show you the first bit really, just moving these drops of liquid around on the device, mixing them, reading out the output, which is a colorimetric or a fluorescent output. And this is all done in real time. And this assay took 15 minutes from urine to answer. So that was the device. Great stuff, worked, but you'd never sell it because in many ways, too complicated. Oh, this shows how you mix fluids, fine. So worked with Sharp to develop that, and they set up a company called AQDrop, which commercialized this whole technology. Pre-COVID, you can now buy this. If any of you know about Oxford Nanopore Technology, ONT, they do rapid sequencing. Part of the toolkit from ONT is this device called a Voltrax. It's in its second generation. What it does is it takes a sample, chops it up, extracts the DNA, does what's called a library prep, and throws that into the Oxford Nanopore sequencing unit. So that's actually a commercialized piece of technology based on large area programmable digital microfluidics. So I then carried on working with another company called E-Ink, and maybe very few of you have heard of E-Ink, but you've all heard of the Amazon Kindle. And the Amazon Kindle is also display technology, which is driven by the same transistor backplane, TFT transistors. But it's much, much cheaper than an iPhone display, for example. It's very basic. It's made on amorphous silicon. And I started to work with E-Ink to develop a parallel technology, and a company in Cambridge called Nuclera. And they were interested in doing something that's called cell-free protein expression. So in biology, a cell will make proteins going from RNA to the machinery, or DNA, RNA, machinery, proteins. Right? It turns out, if you're not a biologist, that you can do this without the need for a cell using just the chemicals and the machines. You extract them, the ribosomes, and so forth. So this cartoon here shows you the plasmid, that's the DNA. You use the machinery, which you can buy from companies, in a test tube to create the long polypeptide chain, which then gets assembled into the 3D structure with other proteins. So it's called cell-free protein expression. This is a very long process. If you want to express typically one drug target, it may take you 3 months, 4 months. It's becoming very important as we now move towards personalized therapy. So my immunotherapy may be different from your immunotherapy and so forth. So there's a big market to do this. And I started working then with Nuclera to develop a technology based on this digital microfluidics for doing this very thing, but not producing one protein, but producing 96 different variants of proteins at the same time. And this is the cartridge we developed. You can have a look at it later. This is all made from silicon. It's very, very cheap. And it does what this video is going to show. It does. There's lots and lots of holes here for putting liquids in. It takes the liquids, DNA, ribosomes, other enzymes, nucleases, mixes them in the right proportions, other proteins, and at the end of 24 hours produces 96 different versions, more or less, of the same protein, which you could then take off for doing mass spec or further analysis. It's not large-scale manufacturing. It's for rapid screening of different proteins. That is now sold by Nuclera. I haven't got my watch with me. How much time have I got left? 5 minutes. 5 minutes, OK. So that's one piece of technology. Last 5 minutes, talk about, this is moving fluids. What can you do with moving fluids if you commercialize the system? Talk about technology we've been developing for about 10 years, which is about analyzing particles. Spent 40 years analyzing the properties, the electric properties of particles. We've come up with a new method of analyzing whether or not bacteria are resistant or not resistant to antibiotics. We've all heard about antimicrobial resistance, I hope. It's the next pandemic, people say. It's claimed by 2050 it'll be the primary cause of death. It's already now claiming 1 million deaths per annum, greater than the combined burden of influenza, TB, and HIV, surprisingly. Typically, if you have a urinary tract infection, which is what that shows, sample goes to the lab, gets plated out in agar, then they expose the agar to various antibiotics, little discs. They use something that was invented nearly 100 years ago. They measure the distance away from the disc to which the bugs grow or not grow. with the calipers, and they have the stacks and stacks of plates, and they still do this with calipers, right? It's a zone of clearance. It hasn't changed. It takes 3 or 4 days. It's really, really very slow. It's time we were able to do something a bit better than that. And so we came up with a method of doing this based on a electrical cytometric technique. This is a cross-section of a fluidic chip in which there are embedded microelectrodes. And the electrodes are about the same size as a bug. Let's say 10 microns, a bug is a micron. You flow the bugs between the electrodes. You apply a voltage. As the cell flows, it perturbs the electric field. And you measure current change, right? So you can count bugs, but actually you can do more than that, because if you scan through the frequencies, you can characterize the electrical properties of the bugs. So watch this video. We measure 10,000 bugs in about 30 seconds. Now I'm going to expose the bugs to antibiotics. And that bug will change. And the cartoon will show you how it changes. And it's actually what you see if you look down the microscope. First of all, you get this little bleb out to the side that's at the zone where the bug divides. That gets bigger and bigger and bigger. And eventually, if you wait long enough, the bug forms a very large spherical object, and then it explodes and disappears. All of that takes less than 1 cell division, half an hour. And you can track that electrically with this device. So you expose the bugs to antibiotics, you wait half an hour, and you measure what's there. And they change in shape, they change in electrical properties, they become leaky, or they actually explode and disappear. And this is a scattergram. I haven't got time to explain what it is. On the left-hand side is a control scattergram for either bugs that are not exposed to antibiotics or are resistant. On the right-hand side are bugs that are susceptible. They basically move one way or the other, or they disappear, right? This next one is a clinical sample. And I don't think I need to tell you which one is the susceptible one, and you don't need machine learning or artificial intelligence to work that one out either. It's that one there, meropenem, right? So this is a blood-borne infection, bacteremia. This is from a clinical sample in the hospital in Southampton. That patient had a bacteremia that was resistant to all those antibiotics except meropenem. Now that would have taken 3 or 4 days to diagnose. This was done in 3 hours. And we're now commercializing that technology. So the one thing about commercializing is you go from that top left-hand image there, which is where we started a 1.5 years ago, into the bottom image, which is what commercial money allowed us to do. Not just the money, but actually being outside the university system where you can speed up all of this kind of thing. We made 3 machines. We've done clinical trials. We've got 98% concordance with standards in 3 hours instead of 3 days. And we're now doing FTA, CA mark approval. And we hope to get a UK product launched by the end of 2025. And I think that's my last slide, except to thank all the colleagues that worked with me, particularly the guys from Sharp, UK Health Security Agency in Porton Down, where we collaborated on the work with the bugs, and the companies, Nuclera in Cambridge, and funding from various sources. And thank you very much. I'll take any questions if there are.
Okay, now it's question time. Anyone has a question? Maybe start from me.
It's coffee time, it's fine.
So my question is that I did some work on the EWOD and plus SAW. So I'm just feeling that because the electrowetting, we need to treat the surface with hydrophobic.
You're absolutely right, yeah.
Yeah, but once you're working with sometimes maybe there's degradation,
yeah.
Would that be a potential trouble?
So it depends if you're doing this as a research or if you're doing it as a commercial company that you want to make money. So if you're a company, it's good that it degrades because you can sell more cartridges.
Okay, so you can sell more, right?
Exactly.
Okay.
So you do use them only once and then you throw them away.
Okay, that's good strategy. Any other question? So if no questions, so let's thank Howard again.
Yeah, thank you.
Thank you. Yeah. So there is a product which you can look around. Yeah. Okay. So now let's move on to the this session's last talk from Professor Megan Povey from University of Leeds. It's about acoustic and urology determination of elastic property of soft materials. Please.
Thank you to Mehdi and Acoustofluidics SIG for inviting me to present some recent work by myself and colleagues. I'm Professor of Food Physics at the University of Leeds, and my interests over decades have been developing measurement techniques that are economic and can be used in low margin industries like the food industry. So there isn't much money to be spent on sensors, but sensing is very important. If you're talking about food chain, tracing, the integrity of the food, our health, so there is an issue there. I've been particularly interested in using acoustics over the years because of its potential to be used non-invasively, because of its potential to work in optically opaque systems. It can be used externally to pipes, it can be retrofitted, and the sensors can be quite economic. So one of the interests over the years has been using acoustics to measure rheology, the flow properties of materials, and again doing this economically. And so this is what prompted this piece of work. Now, we're interested in complex, heterogeneous materials where structure emerges during the processing. And it's important to understand that the structure emerges on different scales. So as the scale increases, there are qualitative changes. This is one of the reasons why scale-up is very difficult, because the rules that apply, say, at the molecular level, as a mesoscopic order emerges, new rules, new laws apply that you can't actually predict. And so this is an example of actually a fatty spread, you know, a margarine or something like that. But actually the way the structure emerges in that product is very complex. It goes right back down to the structure of a triglyceride and the way those triglycerides pack in the fluid state. So we also have to worry about how the system changes as it cools, as it crystallizes, and it's the emergence of the crystalline order that generates the structure. And this is true in very many foods and very many systems, pharmaceutical products and so on. Okay, so classical rheology involves the measurement of viscosity. Generally, it's an offline measurement where you put the material into an instrument which applies a stress, and that instrument then looks at the response, the strain that appears as a result of the application of that stress. And these equations relate. Oh no, the timer's on. Never mind. Okay, so the left-hand set of equations relate what's called the longitudinal viscosity to the bulk and the shear viscosities. Conventional oscillatory rheometry does not measure bulk viscosity. Bulk viscosity is the elephant in the room of rheology. But with acoustics, we can measure the bulk viscosity. And we can also measure the moduli from the speed of sound. And in soft solids, which mostly we're interested in, then this simplifies to a ratio of the bulk modulus divided by the density. So we've got a set of simple equations which, by the way, Newton's treatment, Newton assumed that the speed of sound was isothermal. He was wrong about that, actually, and it was Laplace who corrected Newton to point out that in most systems, actually, the speed of sound is relating to the adiabatic properties. Now, if we're going to use acoustics and ultrasound, we have to relate the classical rheology, which might be carried out at 1 hertz or 10 hertz or even 100 hertz, but we're making our measurements at hundreds of kilohertz, megahertz. So we need to be able to relate the attenuation to these moduli. So we're trying to establish a relationship between the low frequency rheology and the high frequency acoustic measurements. And we can actually establish the simple relationships between the elastic properties, the real and imaginary part of the elastic properties, and we can actually obtain a frequency-dependent shear. So G double prime is minus I omega eta S. Now, this all looks straightforward. When you're actually doing this, in reality, it's not so straightforward. Why did that do it all over again? Right, okay. Right, so we'll start applying all this to a proper food, anhydrous milk fat. And anhydrous milk fat is a soft solid whose inhomogeneity is characterized by large crystal clusters. So here is a picture of the melt, and below, 3 degrees lower, the crystal structures are emerging, and this crystal structures contact a sinter, and they impart a rigidity to the material, which we detect when we eat it as softness, but it's nevertheless a solid property. And we've been doing this using acoustic attenuation measurements over quite a wide range of frequency, from excuse me, a few megahertz up to about 120 megahertz, so we can get these attenuation spectra. The kink in the curves that you can see are at the point where these emerging crystal structures are of about the same size as the wavelength in the spectrometer. So that's causing a kind of anomaly in the spectra. So we can obtain from those attenuation spectra what's called the longitudinal viscosity, and and here we see them as a function of frequency. And let's try my magic vacuum cleaner. Okay, so what we have here is a long wavelength, low frequency, and in this region, we've got approximately Newtonian behavior. And then at the higher frequency, shorter wavelengths, we've now got a frequency-dependent, non-Newtonian behavior. So potentially, we can also obtain the shear viscosity using low-frequency rheology, so that if you've got Newtonian behavior, we can use low-frequency oscillatory measurements of shear viscosity. If it's non-Newtonian, you can't. Okay, so where does that leave us? If I remember where. Oh, yeah, I apologize for those who've seen this talk already. I gave it at the European Rheology Conference. Now, we can also measure the speed of sound. And if we measure this from the melt into the crystallized material, we can see in the melt, we get a nice linear response between the speed of sound and the temperature. And this is going up, which means that the elastic moduli are getting higher But this is the region where crystallization occurs. And in that region, you just can't make sensible velocity measurements. And the reason is that the acoustic field is actually interacting with the crystallizing system, actually changes the way things crystallize. But eventually, the structure reemerges, and then we can measure the velocity of sound again. So we can relate the velocity of sound to the real part of the bulk modulus. And so we can start assembling all the rheological characteristics of the material that we're interested in. This is classical rheology, oscillatory rheology. So we start putting all this together, and we can get every single relevant modulus as a function of temperature. So we've got bulk, shear, real and imaginary parts of the elastic modulus, real and imaginary and the complex moduli, shear moduli. We've got the bulk modulus, real and imaginary parts. Density has to be measured separately, and the velocity of sound. So we put all this together, and we've got a picture of the elastic properties of the system. The one flaw in all of this is that we're depending on a low-frequency oscillatory shear measurement of viscosity. But what we can do is we can use probe particles, say silica probe particles, to determine the shear viscosity acoustically as well. So potentially, we can do the whole thing. And this is a concentration ladder. It's a function of attenuation against frequency. And this is the fit for water. So we've actually got the viscosity of water out of this within about 10%, which, if you ever try to measure the viscosity of water, is not bad. Okay, so I think all that remains is for me to linear term. Oh yes, sorry. Okay, well, this uses scattering theory, so it's a little bit complicated. Yeah, there's the value for the viscosity. Excuse me. Right, so conclusion. Acoustic rheology can be non-invasive, inline, and fast. Bulk, elastic, and viscous terms are much larger than their shear counterparts and relate strongly to the bulk properties, the component phases of a mixture. And finally, acoustic microrheology can potentially probe changes in shear viscosity and in process analytical technology. So this work involved a big collaboration. There's actually a lot of theoretical modeling work has gone into it. So thank you to all my colleagues, and thank you for listening.
Much, yeah. So now it's open for question. Anyone? Yeah.
Thank you very much. I just have like two questions. The first is, can we use this method for non-Newtonian liquids when we have like polymers in them instead of soft fluids?
Yes.
Soft solid, sorry.
This is a sort of a rigorous theoretical treatment. Actually, you can start using machine intelligence, artificial intelligence, machine learning to correlate the acoustic measurements. So you might not have your shear microviscosity measurements, but you still understand, you can know how your process is reacting to the different process conditions, and then you can build correlations. The importance of this is to show that there are good physical reasons to think that the attenuation and velocity of sound are strongly related to the rheology of the system. So even if you can't measure it absolutely, you'll certainly be able to see changes in the viscosity, which often, if you're in process analytic technology, you're working with thousands of tons of material, that is worth $1 million.
Thank you.
Another question. Maybe I ask, so I'm curious that the temperature is just the room temperature, the changing, because it's 22 degrees C. Is there any physical or kind of biological reason why there is the changing just at that temperature?
Oh, well, it just happens to be the melting point of anhydrous milk fat. Okay.
Oh,
so you start with the melt, say it's 60 degrees. We cool it, and it will begin to nucleate. So at that point, you begin to get solid appearing, but it doesn't begin to change the shear rheology until the crystals begin to network and sinter. Okay. And at that point, you get a space-filling network. And the one reason it is about mouthfeel, because we want things that, when you heat, it melts at a higher temperature than it crystallizes. Yeah. So during manufacturing, you're interested in the crystallization, but when we eat fats, we want them to melt nicely. So chocolate, for example, has this wonderful property of melting in the mouth and cooling and making you happy all at once.
Okay, yeah. So it's special for that milk, that type of milk?
It's just for that type of milk.
Yeah, okay,
yeah. So, sure. I mean, it just happened to be paid for by a milk company.
Okay.
And they supplied the anhydrous milk fat. And it was a sort of great example of a tough, soft, solid problem.
Okay. Okay, thank you very much.
You have to do it for real when you're doing it for food.
Okay. Yeah, thank you, Megan. Yeah. Okay, now is for a short break. And after break, we'll have the next session. Yeah.
Next, we have Dr. Friya Hossain from UCL, and he's going to talk on advanced ultrasound techniques for complex multi-phase flows.
Thank you for the presentation. My name is Friya. I'm from UCL. So with fluid dynamics, recently, or most useful techniques to characterize complex flows is that they use a PIV and X-ray, MRI, certain techniques to characterize the dispersions, but they are limited to, for example, optics. They need a transparent X-section, which is not valuable for industrials. Gamma ray and X-ray forming radiations. So as an alternative, we developed the ultrasound techniques to characterize the dispersion in complex flows. So we applied the techniques to different areas, which we use it in fluidizations when solid liquid and solid gas flows, in microfluidics channels, in suspensions and pipe flows. So we developed the techniques in different areas, which I'm showing you here what we did. So experimentally, we started experiments on small channels where we have a oil drop dispersion in small channels, like 0.5 millimeter of the tube inner diameters. We also applied to the systems where it was a large pipe with 26 millimeter in diameters, and also the dispersion of drops in a stirred vessel, which is a 5 centimeter in diameter, and a large scale of fluidizations, which we have a very dense particle packet in a bed, and solid liquid and solid gas flows as well. So for these, we made different parameter characterizations. At first, we started with applying to solid liquid fluidizations, where solid particles packed in a bed and water flows, and the particles start to expand, and then the concentration is changed, and then we measure the different parameters. We analyzed the voidage of the bed with sound speed, so we used the sound speed to measure the voidage of the bed. We used the Doppler principle effect to calculate the velocity profile. In this fluidized bed, when the fluid flows, these particles moving up and down. They won't go anywhere. They're circulating inside. So we use the Doppler effect principle when we send the signal. Ultrasound signal interacted with moving particles. So those particles moving upward or towards the sensor, the reflected signal of those moved particles larger than the emitted signal. When the particles move downward, we found that a scattered signal frequency is smaller than the emitted signal. Therefore, we use this principle to calculate the velocity profile of this particle. What we found out, the particles moving upward from the center of the pipe and down from the side. Then we went to measure the particle size distributions, this is very high concentrated, up to like 60% of the concentrations. So we use the ultrasound technique to measure the size distributions. We send the signal with different frequency ranges, and we obtained the attenuation of the signal. When the signal propagated through the dispersion tract with particles, it depends on the particle size and density, the attenuation changes. So we tested 3 different samples. For each sample, we obtained the size distributions, and then we mixed all the 3 samples. Then we used ultrasound to measure the size distribution, which we found that capable of measuring different size distributions, which we, in fact, in our published paper, we validated it with a microscope imaging that was a good agreement. So when we move it to the solid gas flows, we found that the ultrasound is highly attenuated in air. So therefore, we could not use the ultrasound there. What we did is we actually listened to the sound generated from the system. When the fluid flows here, particles are colliding and friction with in each other and in a tube wall. That way they generate elastic waves. So we use an acoustic emission sensor that we listen to the signal generated from these collision and frictions. What we found out here is we tested 4 different samples, which their size distribution also analyzed it here. We found out that for larger samples, the larger acoustic emission amplitude generated from fluidizations. And also when you increase the fluid flow rates, we found out that the signal amplitude is increasing. Basically, it's when two objects colliding. If they collide, if their size is larger, they generate larger acoustic amplitudes. If they collide faster as well, they also generate a larger amplitude. And then we derived algorithms, which I didn't show it here. It's published in our paper as well. A little bit complex. We inverted this acoustic emission signal to a particle size distribution in a solid gas system. Here, what you can see, the bars are measured from microscope image, and the lines from the acoustic sensor. And then we went to apply the ultrasound technique we have it to liquid-liquid systems. We started with detecting interface heights between two flows, where we have here water and oil, and we send the signal from one transmitter and receiver. Simply you see the signal, detecting the oil and water, which you can measure the concentration of each and measure the interface. This is from imaging. So this is a comparison between the ultrasound and imaging. You can see with a good agreement between both two. And then we went to measuring the drop concentration in stirred vessels. What we have here, the impeller is basically first, we position it at the interface first between the two fluids, and then we position it below the interface of the two fluids. When the impeller starts to rotate, it creates number of drops. The faster they rotate, the more drops created. So then we use ultrasound to measure the sound speed in this scenario. So first we measure the sound speed in continuous phase only, which is in case is water, and then we measure the sound speed in dispersive phase and then in a dispersion. And we use these equations to obtain the volume fractions of drops here. So what we can see that the volume fraction measured by the ultrasound compared with laser-induced fluorescence, which we use it to validate the results. And you find a great agreement between these two. These are when the impeller at the top, the interface between the two liquids. These blues were the impeller much down below the interfaces. And then we went to measure the velocity profile of these oil drops in small channel flows, like 0.5 millimeters. So what we did is we first send the signal as before I explained it through the mixture. Then the signal reflected, and we used the Doppler principle to extract the Doppler signal, and then measuring the Doppler frequency, the frequency of the reflected signal from the moved drops, and to be able to allow us to measure the velocity profiles in that very small channels. So these equations, I don't have to go through it because I'm sure you are familiar with it. V is the velocity of the moving drops, C is the sound speed, and theta is an inclination angle for the sensor, and F naught is the emitting frequency, or FD is a Doppler frequency. And then we measure the velocity profile for different flow rates in small channels. We went to a little bit test on a little bit complex system where we first set it on a liquid oil flows where particle dispersed in oil, and we measured the velocity profile with both PIV and ultrasound, and validated the ultrasound result with the PIV, which we find a great agreement. And later we had oil flows and water flows in the other side, and we had a particle dispersed in water layer. And that way, we used the ultrasound Doppler effect to measure the velocity profile only of these particles. So we have a particle dispersed in water, oil on the top flows, they are laminar flows. So what we found out is the blue one is the velocity profile measured by the ultrasound, and the red one is a PIV, which we use it to measure the velocity profile. What we can find out is the ultrasound is able to measure the velocity of the particles close to the pipe, while the PIV cannot do that. We also measured these drop size distributions in different systems. We measured in pipe flows, stirred vessel, but I just a little bit explain how we did this. what we first did is we send the signal through the continuous phase only. We measure the signal amplitude, and then we have the dispersion. We send the signal through the dispersion, and we measure the signal amplitude, and that way we found the attenuation of the signal. And when you found the attenuation, this is extension coefficient, which I have a equation later I can show you. This F is a frequency size distributions. So we had this equation to obtain the size distributions, which we can see here in more details. But when we use this equation, we had a little bit problem with calculations. We had, like, for example, 8 different frequencies of different signals. We got like 8 by 8 matrix with sometimes negative values. So we have used it, this one, the below one, to overcome this problem to get a nice results. Here is alpha is experimentally measured the attenuation coefficient. A is a extinction coefficient. Gamma is a Lagrangian multiplier, and H is a identity matrix. And we have measured the drop sizes for different impeller rotations, and we validated these results with laser-induced fluorescence, which we should be able to see from here. So this is from the stirred vessel. The red one is from the ultrasound measurements, and the blue one is from the pulsed laser-induced fluorescence. We used the similar method, same algorithms, for different dispersion. This is a small channel where we have 0.5 millimeter small channels, drop dispersions. We measured with ultrasound as a blue line. We validated the results we used the high-speed camera, which you can see the image. And we also use it in a pipe flows. So we use it in different systems, different configurations, and we found that ultrasound is actually highly effective for characterizing the multi-phase flows, and as an alternative tool for fluid dynamics, because as I said earlier, with radiations and transparent excitation for optics and limitation on the concentration, so the ultrasound technique is more much better, and also is less expensive compared to MRI and X-ray stuff. And then what we did, we have used the machine learning to, instead of going through the complicated algorithms to process the data, we used the machine learning for the prediction with the ultrasound data. This is again, this is a stirred vessel. This is the particles dispersed in this stirred vessel with impeller rotations. We send this ultrasound signal through this dispersion with different number of frequencies. Then we recorded the signal via the oscilloscope, and we digitized the data for processing. What we can see here is a signal measured in the black one is where there's no particles dispersed. The blue one where you have a dispersions. So we tested 3 different samples with different ranges. First, we measured the sizes with sieves, and then we used the microscope to capture the image of each samples and process it to calculate the size distributions. Now what we do is, we do with ultrasound and a machine learning, and we compared all 3 of them. So we have a measurement with ultrasound, with a microscope, and also the processing using the machine learning algorithm to predict the size distribution as well. So in here, for the machine learning setup, we had a signal in when you have no particles. When a signal, we have a dispersions for a range of frequencies as an input. Then that way we calculate the attenuation coefficient. Well, D is inner diameter of the vessel. So this is this equation where phi is a volume fraction, is a wave number k, and an calculated from these equations, which parameters are detailed below here. And then we use it attenuation, this from the equation, and the number of frequencies we input, like 1 megahertz, 10 megahertz, the number of frequencies we added to it. To a random forest, we use the random forest algorithms to predict the size distribution, and use the microscope imaging as a true size. And then later, I'll show you, we've compared 3 of them: the ultrasound, the machine learning, and the microscope. And these equations where we calculated the drop size distribution with the particle size distribution with the ultrasound technique, which in here, Mn is just, I write in different letters. Mn is the same as this one. G is the attenuation coefficient, and again, gamma is the Lagrangian multiplier. So first, what we can see is a prediction from machine learning for each samples. The red line is what we have from the microscope. This is a true values. The blue one is predicted from the machine learning algorithm. We can find it with less than 2% error, the accuracy of the measurements for each 3 samples. And then when we compared with ultrasound, we have used the log normal distribution to compare all the 3 different measurements. What we can see here, this is the black one is what is measured by the microscope. The red bar, which is predicted by the machine learning algorithm. And the blue one is what is measured by the ultrasound algorithms we developed. So you can see that with the machine learning, you could have enough better accuracy with the ultrasound data to do the particle distribution, and it's very quick. It's a matter of 1 minute. And here, so we tested the ultrasound and acoustic emission on many different systems, different congregations. We are able to characterize size, concentrations, and velocity profiles. And thank you very much.
Thank you very much. Questions? We have one question from Despina.
Hi.
Thanks. Apologies if you have mentioned it and I lost it. You have tried liquid in liquid.
Yes.
And solid in liquid.
Yes.
Have you tried liquid with solid? So basically kerosene with water and particles.
We tried something like this. This one. We have a oil, water, and particle.
And could you distinguish between the 3?
Yes.
Accurately?
So you want to measure this size, or what parameters you want to measure, for example?
As much as possible.
Okay, so here, for measuring the velocity profile, you need to have a scatter in a phase. For the oil phase, you need to have like a drop or something for velocity profile measurement. You cannot measure the velocity profile without having scatter. Only you can measure the average velocity. For size distributions, you can measure the size distribution if you have a drop seen as a phase, particle in as a phase. That way is not a problem, because with ultrasound, you can separate the signal, you know where the signal reflected from the interface between them. That way you can measure the size distribution. Concentration, you can measure the sound speed in each of them. You can also measure the concentration. We did with kerosene, we did work with kerosene oil a lot. Recently we have tested some different viscosities, different oils mixed with different viscosities to do the analysis, but I have not presented here.
Okay, thank you very much.
You're welcome.
Thank you very much again, Freya.
Thanks.
That brings us to our last talk of the day.